quantization and self-organizing map and adaptive resonance theory, that is VQ, SOM and ART. Now these three methods, that is your vector quantization and coherent self-organizing map and ART, these three methods are basically used for clustering the neurons, right, for grouping the neurons into a number of clusters. They're usually the two-layer artificial neural network. Only the input data are given, so these are unsupervised learning methods. They are self-organizing output. They will give you the output, and you have to check it whether it is the actual or not by some methods that we are going to tell, and in which cluster they will be, right. There are main two models are there, but before coming to SOM or ART, I just want to tell you that what do you mean by the vector quantization, because before artificial neural network, vector quantization we used to do for the clustering of the neurons, clustering of the any values, not neurons, any values. After the development of the neural network, we used to do this coherent SOM, which is near about based on this vector quantization, and ART is a completely different theory, right. So these are basically used for the clustering applications. Now before going to this vector quantization, I want to just tell you that what are the different clustering models. There are two types of clustering. One is known as your hard clustering, another is known as the soft clustering. But there are different types of models are there. One is your connectivity models. For example, the hierarchical clustering builds models based on the disconnectivity. That means where the connectivity is there, it will be in the one cluster. When there will be discontinuation, again the discontinuation of the link or connectivity, again it will be in the different cluster. Next, another model is your centroid model. If you have done k-means method or the k-means clustering method, you may have done in data mining. If you have read in data mining, then you have this classifier or the clustering models. For example, naive-based classifier or the k-means clustering method. The same method is used here in neural network also for the clustering, and these are basically depending on the centroid algorithm. Next is your distribution model. Clusters in this modeling, clusters are modeled using the statistical distribution, probabilistic distribution or some other statistical distribution, and normal distribution, Gaussian distribution. Like this, they carry out the different clusters. Density models. For the density models, we use the tools such as the DB-scan and the optics. These are used for the clustering or the classification, right. DB-scan is used in image processing also. If you want to do the the recognition of some mammograms or something else, so before doing the classification through the neural network, we can use this DB-scan, which it can be used for the basic pre-processing classification. So DB-scan can be used for the this density model classification. After that, there are subspace models, right. Subspace models in bi-clustering, that will be the two-mode cluster. These are known as your two-mode clusters. These are modeled with both cluster members and the relevant attributes also. Otherwise, group model is there if there is no clustering. That means some algorithm do not provide a refined model for their results, so you can just group it, right. That is a very basic methods of grouping or the clustering. And another is your graph-based model, right. So let us start the vector quantization first. As I have told you, vector quantization doesn't come under the neural network models. Under neural network models, we have only the SOM method, that is coherent, and ART, and the different other methods for clustering, right. Nowadays, SVM classifier is also used for clustering or the classification. Now, vector quantization, it depends on the Euclidean distance. For example, here I have written that D is equal to XP minus CJ. What do you mean by the clustering? Clustering is some neurons in one group. So first of all, for the to start with, what we do, for example, this is your first neuron. So this will be my center, right? This is known as your CJ, that will be the center, right? Now, with this center, that is your CJ, what we can do, that other neurons, whatever present, these are my XJ, for example, these are my XJ. Now what we do, each and every time we do the distance between the CJ and the XJ, we find the Euclidean distance. So here, that's why we have written the formula of Euclidean distance is, it has been represented as the double mod of xp minus cj, right? Double mod of xp minus cj means it is represented as like this, that is your xp minus cj. The formula for the Euclidean distance, it is written as square root of summation of, right? Summation means there are more than one neuron, so 1 to n neurons will be there. So xip minus cji, right? This whole square, right? This is whole square, and I belongs to 1 to n. That means if there are more than one neurons, then the Euclidean distance is your summation of xip, that means x1, x2, x3. These are my x1, x2, x3 different points, or the not neurons, different points, minus the center point, right? And whole square summation of that, and root of the whole summation. So this is known as your Euclidean distance. And in case of Cohen sum also, we will find that we find out the Euclidean distance only. Depending on the Euclidean distance only, we do the clustering. So again, come to the slide. So what we are getting, that this is your actually the Euclidean distance. So what we have to find out, we have to find out that the minimum Euclidean distance from the from the cluster. This is your CJ is your jth cluster. Similarly, we have to find, for example, there are first time there will be one cluster only. After that, you just compare with the one cluster. After that, it may so happen that second cluster also have been formed. Now the points whichever we have, the inputs, you have to compare the Euclidean distance of both the clusters. Now we have to find out the cluster which is giving you the minimum Euclidean distance. So this is the formula, that is your, we have to find out the k where xp minus ck, that is your the Euclidean distance of x from the cluster k is less than xp minus cj. That means or any other cluster, right? So for example, we have find out some cluster which is giving the minimum distance, right? Minimum distance, that means what, that there are more than 3 cluster, and this is my input, right? This is my x, and these are my c1, this is your c2, and this is your c3. Now we have to find out the Euclidean distance of x and c1. We have to find out the Euclidean distance of x and c2. Similarly, we have to find out the Euclidean distance of x and c3. For example, c2, x and c2 is giving the minimum Euclidean distance. So we have find out k is equal to, that means it will be 2. Right? So that's why we can find out that which cluster is giving you the minimum Euclidean distance, and that will be the cluster closer to the input, right? Which input we are checking out, that closer to this input. Now after we find out the minimum distance cluster or the minimum Euclidean distance cluster, then we have to test it with a threshold, right? We have to check it with a threshold, that if it is less than our threshold value, if it is greater than our threshold value. So depending on the value of the threshold, the cluster will be more accurate or the less accurate. That I will come to you, that how we can find out that it will be less accurate or the more accurate. That means if you take the cluster or the row as minimum, then there will be more clusters, because every time it will check with the threshold, and if it is less than threshold, then automatically it will be that cluster only that you have find out the minimum cluster. But if it is greater than threshold, then it will find out the new cluster. So this way the algorithm will go on, and every time the cluster, that is the center of the cluster, will be updated as 1 by n summation of x. But x belongs to Sn, that means the clusters belonging to the clusters, all x nahi hai, the x, all the values of x we will take which are belongs to the same cluster. Then we can find out the center of, the actual center, updated center size, and again the new center will be like this, and again we will find out the Euclidean distance. So this is depending on the Euclidean distance. It will be more clear if we take one example. So this is the example. There are 12 points, right? This is your 1, 2. There are 12 points. This is your 12th point, and in each and every point there is a x and y, right? Each and every point there is an x and y. Now, for example, we have to take rho, that is your threshold. Rho, that is threshold. For example, rho, let us take that it is 2. First of all, we are taking threshold distance equal to 2. Now, how to find out? Let us start with the first point, that is your 2 and 3. So, for the first pattern of 1, right? This is your pattern of 1 assigned to the cluster 1. That means first time it is your first cluster. This is your first cluster. There are no other points. So, first time there will be the origin of the cluster is your cluster 1, where the center is your 2 and 3. So, here the center is your cluster center is your 2 and 3, right? This is the cluster, that is your 2 and 3, and this is your assigned cluster is 1, and this is a pattern 1. Pattern 1 means this is your first pattern we are checking out, right? So, to start with, we are giving the same value as the first point. Now, come to the second. Second is your, that is your second pattern. It is giving the point 3 and 3. X values, the coordinate, it is giving the 3 and 3. Distance, to find out the distance, we want the two coordinates, x1, y1 and the x2, y2. Now, Euclidean distance, it says, as I have told you, that is your x1p minus cj1 whole square. X means it is a pixel point. That means it considers the x plus then another point, right? So, if we distance, to find out the distance between the 3 and 2, because our center point is your Cj is your 2 and 3, right? So, if we find out the distance, what will be the distance then, Euclidean distance? It will be root, it should be root, right? Summation, that means we will do the summation. Xi, our x is your 3, this is your our xi. Cji, that means first time Cji is your 2, right? So, that will be 3 minus 2 whole square. It will be whole square because I have given here, that is your xip minus cji whole square. Then after that we will do the summation. Then again the summation, then again 3 minus 3. So, this is our 3 and this is also our 3. So, it will be 3 minus 3 whole square. That means we are getting only 1. Right? So, in the second case, the Euclidean distance is 1. So, we have found out that Euclidean distance equal to 1. Right? Next condition, what is the condition? That after the finding the Euclidean distance, what we should do? We should test it with the threshold. In our case, threshold is equal to 2. Right? It is telling that if it is less than the threshold, that means distance is less than the threshold distance, then the pattern will be in the kth cluster only. That means whichever cluster we are comparing, right? Now we are comparing with the first cluster. This is your first cluster because we have only one cluster only. So we have found out the distance 1, and this 1 is less than the rho, that is your rho means that is equal to 2. So, it is less than 2, that means 1 is less than 2, that means this pattern belongs to the same cluster, that is your 1 cluster only. Clear? Now it is telling that after you find out that in which cluster it is, after that what you should do? You should find out the new cluster center, right? New cluster point. Now, what will be the new cluster point? It is the average 1 by n summation of x. Now, There will be 2 points definitely. Now what will be the point? Now here we had 2, here we have 3, right? 2 x point and 2 y point. So what will be the average? 2 plus 3 divided by 2. That means there are 2 points. So that will be divided by 2. That will be 2.5. And here that is 3 plus 3 divided by 2. That will be 3. So in the second case, what we are getting for pattern 2, it is assigned to class 1. Because the distance between this and this, it will be 1, which is less than 2. That's why it is on the first cluster. And the cluster center, what will be? It will be the average 1 by nx divided summation of x. That will be 2.5 into n3. Right? These are my new points. Now for the cluster 1, we have the point is your 2.5 and 3.0. The before the 2 and 3, that was omitted. That has been updated, right? Now next is your pattern number 3. So let us take the pattern number 3. For pattern 3, the point is your 2 and 6. Till now also we have only one cluster. We have to check it that this 2 and 6 it will be containing in cluster 1 or it will be some new cluster, right? We have to find out. 2 and 6 are the point. And the Cj is your 2.5 and 3, right? So what will be the distance? Again it will be root, right? It was 2 and 6, sorry. So it was 2 and 6, so distance will be 2 minus 2.5, because here it is a 2.5, 2 minus 2.5 whole square, right? Plus 6, it was 6, now here we have the 3. So 6 minus 3 whole square. So you will be getting 6 minus 3 is 3. 3 square root will be 3 only. And here it will be 0.25, right? When you will add that 3.25 and you will, this will be 3 square. That means 9.25. When you will give the root, you will get the value 3.041381. Whatever you want to take, 3.04 also you can take, or 3.041381 also you can take. So this is our distance. But now this distance will be checked with rho. Our rho is your 2. So it is greater than 2. That means it will not be in the same cluster. It will be the new cluster. So our new cluster, again I have named it, that is your cluster number 2. And for the cluster number 2, what will be the center? The center will be the same point as your x. Because it is a new cluster, you don't have to do the averaging, right? When it will be the same cluster, then only you will do the averaging of every point, right? Now we have only 2 and 6. That means we have the final point 2 and 6. Now for example, this is our 1 and 2. Now let us take the pattern 4. After that 5, 6 and 7 you do it yourself. I will just ask you. So pattern 4, again we are getting, what are the pattern 4? That is your 3 and 6. Now we have the 2 clusters, right? Cluster 1 point is your 2.5 and 3, and cluster 2 point is your 2 and 6. Now for the 2 cases, 2 cluster, we have to find out the distance, right? What will be the distance from the cluster 1? Let us find out the cluster 1. That is the point is your 3 and 6. Okay, then it will be root over of 3 minus 2.5 whole square, right? Plus 3 and 6, 6 minus 3 whole square, right? You will get some value here, right? And for the other case means from the point 2 and 6, what will be the distance? Again, root over, here I am writing, or it is not visible. So if we are writing that root over, here we are writing that root over that is your 3 and 6, I suppose. So 3 minus 2 whole square plus 6 minus 6 whole square, right? That will be 0. That means 3 minus 2 whole square means that will be 1. And this 1 is definitely will be less than this, because here it is 6 minus 3 whole square, right? So whatever it will be less, that cluster we will take. So it will be containing in the cluster number 2 only, because the distance will be 1, and that distance it is 1, and it will be distance from the cluster 2. So that's why this will be belong to the cluster 2, because this is less than rho, that is your rho is your 2. So it will be then the same cluster from which the distance is less. So it will be then the same cluster. Now what will be the cluster center now? The cluster center will be this 2.6 and the average of 3.6, 3 and 6, 2 and 6 and 3 and 6. That means 3 plus 2 divided by 2, that will be 2.5, and 6 plus 6 divided by 2, that will be only 6. Now we are getting that is 2.5 and 6. Like this, we will be doing one by one, and all the points that will be in the 12 point we will do this 12 points, and we will find out that what are the clusters we can find out. If you have understood, you just do for me for 5, 6 and 7. Let us do for 5, 6 and 7. Then it will be clear to you that whether you have understood or not and how to find out the cluster. Then we can match it, and after that I will go on further. So just you take 5 to 10 minutes and you carry on with the work of for 5, 6 and 7. That is a point 6, 3, 7, 3 and 6, 4. I'll ask the remote centers again after 10 minutes. You just do it yourself. If you find any difficulty anytime, you can just call, you can just talk to me. सबको on कर दो.
हेलो मैम, नेक्स्ट स्लाइड पे डाल दीजिएगा. हेलो, गुड मॉर्निंग मैत्री मैम. थैंक यू मैम.
Just 1 minute. Just 1 minute. This one, is it visible to you? Is this visible to you?
Yes, ma'am.
Okay. Just you write the point first. For the 5, that is 6, 3. For 6, it is 7, 3. And for 7, it is 6, 4. Right? These are the 3 points. And this also you will need. You just write down the points up to 7. After that, I will put it in the next slide. You have written? Okay, let me give you to the next slide. Now you do it.
Hello. Hello. Good morning, ma'am.
Good morning, Ji.
Ma'am, would you tell this cluster number 1 and cluster number 2? What are the points? Means from which we have to distance.
For cluster number 1, the point has come to 2.5 and 3. Just let me just remove this thing. Just 1 minute. So this is your slide. So for the cluster number 1, after the second pattern, we have got the cluster center as 2.5 and 3.
Okay, and for the second?
Right. And for the second, we have got, after pattern 4, we have got the modified one, that is 2.5 and 6.
Okay.
Cluster center, modified one, right? And you have taken these values, that is 1 to 7 values that you have taken.
5, 6 and 7 I have taken.
5, 6, 7, 1, 2, 3, 4, 5 also you may require, but sorry, 1, 2, 3, 4. You may not require, but anyway, you can just note down these values also.
Yeah, I have noted down 5, 6 and 7. I will calculate.
Okay, okay.
Thank you.
Maybe pattern 5, yes. 6 and 3, and distance is 3.5. समझ आ गई? 3.5. क्लस्टर 2 के लिए हो गया ना, ये क्लस्टर 2 और क्लस्टर 1 के लिए कितना था, ये 2.5 एंड 3 था, वो भी तो माइनस करनी पड़ेगी ना, तो मिनिमम होगा वही लेना है। ये तो फर्स्ट क्लस्टर का फाइनली आ गया था 2.5 एंड 3, सेकंड क्लस्टर आफ्टर पैटर्न 4 आ गया था 2.5 एंड 6, ये आया था ना, ठीक है। अब जब आप फिफ्थ वाला नंबर कितना था, 6 एंड 3, तो ये दोनों से माइनस करना पड़ेगा ना, दैट मींस 6 माइनस 2.5 होल स्क्वायर प्लस 3 माइनस 3 होल स्क्वायर, ठीक है। तो ये एक आ जाएगा कोई भी डिस्टेंस, फिर ये आ जाएगा 2.5, हाँ 6 माइनस 2.5 एंड 3 माइनस 6, तो दोनों में जो मिनिमम होगा वो लेना पड़ेगा, ठीक है। फिर मिनिमम होने के बावजूद भी देखना पड़ेगा कि इट इज ग्रेटर देन रो या लेस देन रो।
Hello. Hello. Hello, ma'am.
हेलो, यस,
Ma'am, the value of center same for all. Hello.
आप सिस्टम के सामने आइए, आपका आवाज नहीं क्लियर है। अभी रिकॉर्डिंग में ऑफ कर देना, फिर जब शुरू करोगे ना।
Hello.
हेलो, हाँ जी हाँ जी, बताइए।
Ma'am, the centered value of centered is same for all. That is 2.5 and 3. Hello. Hello.
हेलो,
Ma'am, the value of centered, that is D, is same for all.
पी,
The value of D, that is centered, is same for all. That is 2.5.
हेलो
हेलो, हाँ जी, समझ नहीं आ रहा, आपका आवाज नहीं आ रही है।
Ma'am, the value of
जी मैम,
centroid.
वैल्यू ऑफ
हेलो
सेंट्रोइड आफ्टर फिफ्थ,
Yes, yes.
आफ्टर फिफ्थ मैम इट इज 4.25 एंड 3।
आफ्टर
हेलो
फिफ्थ, नो 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 नो, इट विल बी 6 and 3.
6 and 3,
Yes,
हाउ इट इज
it will
मैम?
be it will be in the new cluster number 3.
क्लस्टर नंबर 3,
Yes, it will be in the new cluster.
ओके।
Huh?
आवाज कहीं मर गई।
You have told the pattern 6 or pattern 5?
पैटर्न 5 मैम।
Pattern 5, it will be the centroid will be 6 and 3, and it will belong to the new cluster that is equal to 3. Let me just do it.
इसका देखिए साउंड कम कर रखा है क्या वहाँ से भाई।
इसके रिकॉर्डिंग में डाल दो इसका, हरजो रिकॉर्डिंग।
हेलो
Yes.
मैम जब हम पैटर्न 4 का कर रहे हैं तो पैटर्न 4 से हम जो यूक्लिडियन डिस्टेंस है वो 3 और 2 के साथ कंपेयर करेंगे ना?
मैं जस्ट एक बार बता देती हूँ आपको। फिफ्थ के लिए, फिफ्थ पैटर्न के लिए the points are 6 and 3, that is your x coordinate and the y coordinate, right?
जी मैम।
So
Okay.
we have till now we have the two clusters we got. One is your C1, another is your C2, and this is my fifth point. I have to just check it that whether it is under C1 or it belongs to C2. Now in
Okay.
C1, after pattern 2, you can just check it. After pattern 2, the C1 has been modified to, I suppose, 2.5 and 3.
2.5 and 6.
Right? 2.5 and
Yes.
3.
Yes.
है ना? And in C2, after pattern 4, we have modified to 2.5 and 6.
Yes ma'am.
Right? Now we have to
Right.
find out the distance. Now how to find out the distance? Our point is 6 and 3. There will be two Euclidean distance. From C1, when we find out the Euclidean distance, what will be there? 6 minus 2.5 whole square plus 3 minus 3 whole square. That will be easier. 3.5 whole square. 3.5
Okay,
whole square, that will be equal to only 3.5. That will be the Euclidean distance of C1 and 5. Now we
Okay.
have to find out C2 and 5. Again, the C2 and 5 will be 6 minus 2.5 whole square plus 3 minus 6 whole square. That will be definitely, you can find out the value, that will be definitely will be greater than is your 3.5. That means the minimum Euclidean distance is 3.5, which is from C1. Right?
Okay.
That means minimum distance will be Euclidean distance for pattern 5 will be 3.5. But after that, we cannot just determine that it will belong to C1 only, because we have to check with rho. Our threshold is equal to 2. So since this 3.5 is greater than 2, that means it will again it will prepare a new cluster for it because it is greater than the threshold. So this 5 will belong to another cluster, that will be your C3. It will form a new cluster C3. Now when it will find out the C3, then finally what will be the cluster center of C3? Because till now we have got C1 equal to 2.5 and 3, C2 we have got 2.5 and 6. Now we have find out C3 with 5. Now in 5, what was the center? Since it is a new center, so it was x and y was 6 and 3. So for C3, the center coordinate will be 6 and 3 because it is into the new cluster. Have you understood that? Have you understood? Now you do it for the pattern 6. Pattern 6 and 7, I suppose now it will not be any problem. You just carry out for pattern 6. कौन सी clusters?
Hello, ma'am.
This
Hello. Cluster will
कौन
be
सी
3.
cluster से कम है?
Ma'am, cluster will be 3.
For pattern 6?
Yes, ma'am. Cluster will be
Yes.
3
Yes.
and center will be 6.5 and 3.
Very good. Perfectly all right. So for pattern 6, we are getting that it will belong to cluster 3 and the distance will be only 1 and the cluster center will be 6.5 and 3.
Yes,
Right?
ma'am.
And you do it for 7 because 7 में कुछ catch है.
7?
Then let us see.
For 7, cluster will be same 3
3. Yes. Distance.
and distance will be 1.25. No, distance will be 1.11.
Very good. And what will be the cluster center?
Center will be 3.5. No, कितना होगा average? Ma'am, I haven't calculated yet.
आप कैलकुलेट करें.
Hello. कितना होगा average?
6.33.
It will be 6.5 and
Not
3.5.
6.5. No. Not 6.5. It will be 6.33 because the cluster 3 final center you have got 6.5 and 3, right?
Yes, ma'am.
So you have to do the average of these two. For 7 we have got x coordinate is 6 and for cluster center we have got 6.5. So 6 plus 6.5,
Yeah.
that is your 12.5 whole square plus, right? 12.5 whole square, then it will be, 12.5 whole square, then it will be root. No.
6 plus 6.5 divided by 2.
Yes.
It will be 6.2. 6.2 and 3.5.
No. Just 1 minute. For pattern 7 you are doing, na?
Yes, ma'am.
It will be pattern 5 is your 5, 6, 7 are your this thing 6, 12, the 19.
It's 9.5. 6.25. Average of 6.5 and 6 ka average.
No. You must have misunderstood the how it will find out the center. Center is basically, you can just note it here. Center, to find out the center, what we should do, that summation of x, right? It is giving the summation of x. That is your
Same में.
summation of x by n. Right? Summation of x, it will not count the center. It will add the x point of those clusters which are in the same cluster. That means in our case 5, 6 and 7, these three are in the same cluster, right? So what will be the new center? New center is not the average of the center point. New center is your, that is 6 plus 7 plus 6.
So it is 6.33 and 3.33.
Yes, it should be 6.33 and 3.33. Absolutely right. Now I have got it. Now when we'll find out the pattern, we will check the distance between the centers, right? But when we'll find out the updated center, then it will be the plus of these 2 points, right? In previous also we have done like this only. You see, for after pattern 2, we have found out 2 plus 3 divided by 2, that is your 2.5, and 3 plus 3 divided by 2, that is your 3. So after pattern 2 C1 we have got 2.5 and 3. And since pattern 3 and 4 were into the cluster number 2, right? So in that case also after pattern 4, when we have updated the center, we have done 2 plus 3 divided by 2, that is your 2.5, and 6 plus 6 divided by 2, that is your 6. Right? That means 2.5 and 6. But in this case, when we'll find out the updated center, so we have the 3 points. So we have to do the plus and then average. Similarly for 6 plus 7 plus 6, that will be 6 plus 7 plus 6 divided by 3, and another will be 3 plus 4 divided by 3. That will be here, you will get 6.33, here you will get 3.33.
Hello.
Hello, yes ma'am?
Ma'am, we have just calculated the cluster for 6th point. So when we will calculate the for the point 7, so it will be the average for 5th and 6th point. when we are finding the center of the cluster, it would be 6 plus 7 divided by 2 and 3 plus 3 divided by 2. So why we are adding the 7th point? We have to still calculate for the 7th point.
No, we are calculating the center point of the 7 only for the next purpose. We have already calculated after pattern 6, we have already calculated the cluster center, that when we are telling that it is under the cluster number 3 and the new center will be your 6.5 and 3, that we have already calculated for cluster 6, sorry, pattern 6. Now when we are calculating for pattern 7, it is telling that for pattern 7, when we have found out that it is in the cluster number 3, the updated cluster center of pattern 7 we have to find out. That is cluster 3 after 7. Right? So pattern...
Hello?
Yes.
Ma'am, to calculate it for the 7th point, we will just take the average of 5th and 6th point only. So why we are adding 7th point also to calculate the centroid cluster?
Because it is the current point. This is the current point. So after the current point also it should be included. What are the cluster point? It should be included again. Because you see, after we have done the pattern 2, after we have done what we have done, this is your cluster 1, that is your 1, and after pattern 2 we have found out that it also belongs to cluster 1. Then after that we have found out the new cluster center, and to find out the new cluster center after pattern 2, we have to add both these two, and we have to add both these two and the average. Similarly, for 3rd and 4, after pattern 4, we have done the 3 and 4 plus and this plus.
Yes.
After pattern 6, we have only 2 points. That's why we have done these 2 and these 2. Right? 6 and 7 by 2, that is your 13 by 2, that is your 6.5, and 3 plus 3 by 2, that is your 3. But when we are saying that 7th is also into the cluster 3, so we have now 3 points, this and this. So finally, when after 7 we have to find out, we have to do the average of these 3
points. Right. Thank you, ma'am. Clear.
Thank you. Okay. Any doubt from any center that how we have found out the cluster? Now, when we will do the each and every point, you will see this 3 cluster, that means C1, C2 and C3, and some points will be on the cluster 1, some points will be on the cluster 2, and some points will be on the cluster 3. Some points means maybe 1, 5, 6 and 7, whatever you have calculated, that will be in the cluster 1, cluster 2 and cluster 3. Now, what will be the effect of row? We have found out that because we cannot calculate all the values for all rows, so it has been shown that if row is greater, if row values is large, then the cluster point will be minimum. That means if row is your, for example, 4, then you may get the 2 clusters. That means the classification will not be accurate, clustering will not be accurate. If you give another more values, that means, for example, you are taking row is equal to, for example, 8, then you may get only 1 cluster only. That means all the points will be in the only 1 cluster. That means clustering is not accurate. So depending on the value of the threshold, the clusters will be, accurate. But definitely you should take the row value as an optimum value, so that there should not be any small cluster also, that is 1.1 cluster, 2.2 cluster. This should not be like this also, right? So this is about the vector quantization, and I am sure that you have understood it for clustering this. Now let us go for the another clustering, that is your Kohanen self-organizing map, right? So this comes under neural network. So Kohanen in 1984, he has developed this self-organizing map for clustering purpose only. But he also takes care of this Euclidean distance. Somewhat you will find out that there will be similarity, but here we will have the weight updation. Till now in vector quantization there was no weight was connected, because that was not, neuron was not taken into point. Now we will take the neurons or the layers, we will take into point. So there will be the input layer and the output layer fully connected, and there will be delta rule learning. That means something different we will find out in the weight updation. right? Weight updation will be with the help of the delta rule learning. So let us see that what will be there. You can find out here also that, let me just change the ink color. So you will find out that this is also the Euclidean delta W, and here we will find out the Euclidean distance only, that will come out. Only weights of the winning neuron and its neighbors are updated. 1 point. I will just explain that what you mean by this. Only weights of winning neuron and its neighbors are updated. That means if the winning neuron is 1 or some cluster or C1, that means only the neurons with that cluster which are connected with that cluster, only those neurons will be updated. Weights of winning neuron brought closer to the input pattern, right? From the diagram onwards, you can just see if we have can get the in self-organizing map. That means map means it will be somewhat, you know, that you should connect in a somewhat map. This is your map, right, within some area. Now in some self-organizing map, we can have the hexagonal shape, or we can get the square shape, right? These two shapes we can get for the mapping of the neurons. Here in the example, I have shown the square mapping, right? Square shape. Now you can get, okay, this is your actual neurons, and we have to come to the you know, the center neuron, right? We have to come to the center neuron, or we have to come to the closer to the input pattern. So one by one we will do. First of all, we will group. Again we will you know, reduce the radius. Again we will come to this one. Again we will reduce the radius depending on some calculation. Again we will come to this center, and finally we will again reduce the area, and for example you can come to the closer to this input. That way we come to the closer to the input pattern. Our aim is to bring the winning neuron to the closest pattern, that means closest cluster, right? Whatever may be cluster. That means if your cluster is C1, C2, C3 and C4, and if you have the input patterns, you have to check that all these input patterns belongs to which cluster, right? That was our aim. Now to find out, the training algorithm says that you have to set the learning rate and you have to set the weights. First of all, you have to initialize the weights, or you have to set the learning rate. Stopping condition. Some stopping condition we have to find out that what should be the stopping condition. If the stopping condition is true, then you have to just come out of the loop. If the stopping condition is false, that means you have to do the training again and again so that you can come to closer to this, right? Now each and every time you have to find out the Euclidean distance. That is same here we have done. That is your summation of, that is Wij minus Xi whole square. Squared Euclidean distance. That's why the root portion is not there. That is known as your compute squared Euclidean distance. Beforehand in vector quantization, what we have done? We have done the Euclidean distance, that considers the root of summation of something whole square. But here we have not got the root. That means it is a squared Euclidean distance. I is equal to 1 to n Wij minus Xi. This is your Xi. Wij minus Xi whole square. Right? You can write down. This is your Dj equal to I is equal to 1 to n. That is summation from all the neurons, Wij minus Xi whole square. Now again we have to find out the j for which the Dj is minimum, just like that what we have done in vector quantization. And finally we have to update the weight. That is different here, because in case of vector quantization we have not found out the any weight updation. Now what will be the weight updation? The Wij new will be Wij old plus it is finding the delta rule. As you must be remembering that what was the delta rule? That was alpha into, alpha is your learning rate, or C into, C was your learning rate. Xi minus Wij old, that was the difference, right? Xi, this should be I basically. Xi minus Wij old, and then alpha into this. So this will be the delta learning. That's why it is telling that it considers the delta learning rule, right? And after that, update the learning rate. If you want to update the learning rate, reduce the radius, that means area you should concentrate, and then uske baad, after that again you find out the test for the stopping condition, and finally you have to go to the loop. So this is all about your SOM training algorithm. Now let us do one example. Right? Let us do one example that you can just write down here. There are 5 clusters. If we do the examples, then it will be very clear to you. Right? If we have the 5 clusters, C1, C2, C3, C4 and C5, and U1 and U2, these are my 2 neurons, right? So these are the points, that is a point 2, point 3, point 6, you bring to the slide, otherwise it will not be visible, I think. Right. So is it clear to you? You can just note down, that is U1 and U2, you just draw it, and there are 5 clusters, right? And the values are, I am just telling you, that is a point 2, point 3, this is point 2, this is point 3, then U1 and C2, that is your point 6, point 6, it is your point 6, right? Then the U2 and C2, that is your point 5. Then U1 and C3, the weight is your 0.4. This is your 0.4, right? Then U2 and C3, 0.7. U1 and C4, 0.4. This is again 0.4, then 0.6, then 0.2 and 0.8, right? And similar tabular form I have written, that is your 0.2 and 0.3 for the C1, 0.6 and 0.5 for C2, 0.4 and 0.7, this is for C3, 0.4 and 0.6 C4, and 0.2 and 0.8 for C5. And the input, it is telling that input vector is equal to 0.3 and 0.4. Sorry, this is 0.4, 0.4, and learning rate is equal to 0.3. So these are the 3 points we have got. Okay, now let us calculate this one by one. Now what was the point? First of all, what should we find out? If you have the learning rate, what we should find out first? We have to find out the distance, right? Each and every distance we have to find out with this formula. That means D1, D2, D3, D4 and D5. 5 clusters with the input and the squared, right? Squared distance. One thing, one distance I will do for you. You can just check it and finally you calculate for others. This will be D1. What will be D1? It is not root, right? This, like only the whole square and summation. Now our point is your 0.2 and input is your 0.3. That means it is your 0.2 minus 0.3 whole square plus, next point is your 0.3. 0.3, that is your, this is weight, this is your 0.3, 0.3 minus our input is your 0.4, so 0.4 whole square. So this will be your D1, it is coming about 0.02. Similarly, you find D2, D3, D4 and D5. Because we have to find out the distance. This is your distance, so we have to find out according to Wij is your first term, Xi, that is your input in the second term. That's why we have given these weights, the cluster 1 weights, cluster 2 weights. So we have given the weights in the first term and the input, that is your 0.3 in the second term. You do it very quickly and you tell me that what is D2, D3, D4 and D5. उनको ऑन कर देना.
नहीं सुन रहा हूँ. Hello.
Yes, yes. What
The
is D2?
distances are, the D2 is 0.10.
Very good.
D3 is also 0.10.
Yes.
D4 is 0.05.
Something wrong is there. D4 should be 0.40 according to my calculation.
0.05, ma'am. All the candidates are getting the same value in my center.
0.05? Okay.
Yes, ma'am.
Okay.
And the
Then
last value is
D5?
0.17.
This is 0.17.
Yes, ma'am.
Okay. Okay. Now, okay, fine. Other centers must have also got values only. So D1, D2, D3, D4, and D5. After we have found out this thing, what we have written in the algorithm, that we have written. Sorry. We have written that dj equal to this and find the index j for dj is minimum. So in our case dj is minimum, that is for the one case that will be 0.02. That means first cluster distance will be minimum, right? Now what is the next step? Next step is that you have to update the weight. Which weight? Only the C1 weight. You should not update C2, C3, C4 and C5. Only the cluster which is the minimum distance or it belongs to the cluster 1, only that weight you should update. Now what is the formula we have given? So let me just delete again. That is distance is your 0.02. Okay. So let me erase this. Okay. Now what will be the new distance? New distance Wij, right? It is telling Wij. I is your input, that is your only one input only we are taking, that is your 0.3 and 0.4, and j is also in your case is 1. J is also in your case is 1. J is the cluster name and I is your input neuron. In our case only one input neuron is there, so we are taking only W11. So what will be the W1 new? It is telling that W1 new will be W11 old. Right? What will be the weight plus it is telling that alpha into what is the formula? X minus Wij, X minus Wij old. That was the formula, right? Now if we take the value, what we are getting for the two values, that means for the first weight we are calculating. For the first weight, what was the old value? That was your 0.2, right? Plus for the first one, right? For the C1 there are two weights because neighboring weights we should change. So there are, for the C1 there are two neighboring weights. One is a 0.2, another is a 0.3. The first point, that is a 0.2 plus alpha. Alpha is your 0.3, right? And then x is your 0.3, that is your input, only one input, that is your 0.3, minus Wij old values is your again 0.2. So this will be your the actually the W11 new, right? So W11 new will be again with the formula I am again repeating. W11 old, that was old value is your 0.2 plus alpha. Alpha we have taken as a learning rate as your 0.3 within bracket xi minus Wij. In our case xi is your 0.3, Wij old, that means old value is your 0.2. So this W11 new you will get as your 0.23. And similarly W21 new you will get as 0.33. So there will be two values, one will be W11 new and W21 new, right? That means what? For the next training purposes, again we will do the next one, right? For the next neuron, you can say this is only the one neuron. I have shown for the only one neuron. Now when you have got the updated weights, again you have to carry forward with the next neuron, right? You have to train to the next neuron. For the next neuron, what will be the weights? So here it will be 0.23, here it will be 0.33, right? Because new updated weight W11 is your 0.23 and W21 is your 0.33. So again you will get these values, and accordingly again for the next neuron you will calculate again DJ and accordingly which cluster it is, and finally you have to do the weight updation. So just like this you will get that all the neurons you can group it into the only different clusters which are available, right? These are the this is the way of self-organizing map, right? And new weights also we can calculate weight updation, and after that we can calculate for the, you know, if you get the second neuron, if you get the updation of C2, then again the weights connected with C2 it will change, again you will change the whole weight updation, again you will carry on for the third neuron. So similarly you can just group that all the neurons into the different clusters. So this is about the self-organizing map, and for all these you can write the MATLAB programming also depending on your steps, because all these algorithm is there. So to write a MATLAB programming is not a big issue. It is very simple algorithm. So for each and every, you know, you can take, you know, just a set of 3 or 4 neurons, that means two values of all the neurons, and similarly you can take some weights, and how you can calculate this, write the algorithm according to your distance, and you can find out the minimum, then you can find out the old or updated weight, and after that it will belong to the cluster. Then finally you can give in cluster 1 these neurons are present, in cluster 2 these neurons are present, and in cluster 3 these neurons are present. So that will be your complete, you know, self-organizing map. And you can see for this clustering now no desired output or something is needed. You are just doing the unsupervised learning, no teacher, no desired output. You are just calculating and you are putting them into the clusters, right? Now, these are the some applications of SOM, that is your natural language processing, document clustering, document retrieval, automatic query, image segmentation, data mining, fuzzy partitioning, condition action association. So these are different types of SOM applications which are doing by the researchers in this category. Now the next one is your adaptive resonance theory, right? Now adaptive resonance theory, it says that it has been developed by Carpenter and the Grossberg in 1987, right? Now ART, there are main two types of ART, that is your adaptive resonance theory. One for ART1, another for is your ART2. Other ARTs also we are using with fuzzy, with map, all these things ART we are using. But ART1 basically for clustering the binary vectors, and ART2 is for the analog or continuous vector. Just like we have done in vector quantization the analog values, similarly we can do for ART2 is used for the analog or continuous values, and ART1 we use for the binary vectors. Now this is an online clustering algorithm. It is a recurrent type of network. We have already done recurrent type of network, and it is also the competitive output layer. Competition will be done in the output layer, that which cluster is the winning cluster, that cluster will take care of. Data clustering application, it has very specific problem, that is your stability and plasticity dilemma. It is very unique problem in case of ART, that is it should be stable and it should be plastic also. What do you mean by stable? Stable means a pattern should not oscillate among the different clusters. That means when you are clustering, it should not be the case that input pattern I1, it is first time it is coming into the cluster 1, and second time when you are updating again it is coming to the cluster 2, again when you are updating again it is coming to the cluster 3, because every time you will be doing the DJ and you will be finding that. But the distance, here it is not distance, here it is the different thing. So actually the pattern should not be like this, your neural network pattern, that the input already it will oscillate among the different clusters. That means your network should be very stable, it does not change the behavior. Plasticity, on the other hand, it says that if new pattern comes, right, it has the ability of the net, the net has the ability to respond to learn the new patterns, right? If you have the existing pattern, it will learn definitely, but after learning the your network, when new pattern you are inputting, accordingly very accurately it should learn. That means it is plastic. That means general concept, plastic means what? That means you can extend it. Here also it says that it should be adaptive. That means it should have the plasticity. Any situation, any network environment, whatever behavior we change, automatically it should be adaptive and it should calculate. It should not stop. The network should not give that it cannot train the network, or it cannot, you know, validate the value, or it cannot test the value. The network should not give this one. It should be very plastic. Now these 2 points are in, you know, the in a different, just opposite word. One is it is telling that it should be stable, that means it should not change. In another way it is telling that it should be, you know, adaptive. So that means whenever the new pattern we give, it should learn. That means these 2 ways is known as this is your stability plasticity dilemma. So this problem is very unique in ART. So when we design ART, when we you know, do the implementation in ART network with any weight updation or any values, we have to take care of these 2 points. One is your stability, another is your plasticity. Both these should have the optimal value. Then only you can design properly in case of the ART network. So these points is very important in case of the ART. So this is your you know, ART architecture. So in ART architecture we get the 2 you know, the layers, main layers. After that we will enter the another layer. This is one is your F1 layer, and this is your F2 layer. F1 layer is known as your input processing field. That is your where you are inputting, that is your F1. And in F2 these are the clusters, and F2 layer consists of the different types of clusters, and it has a mechanism to control the degree of similarity. That means definitely when you are inputting the pattern, it will say that it is depending on it belongs to cluster 1, or it belongs to cluster 2, or it belongs to cluster 3. So to find out the similarity, degree of similarity of patterns, we find out the vigilance test, and another is a reset mechanism. This is very important module in case of ART, different module. One is your vigilance test, another is your reset mechanism. And 2 types of weights are connected with this. One is your bottom up weight. Bottom up weight means B and IJ, right? I is your input, J is your cluster. And the top down weights, top down is your T, and it is represented as JI. That means it will come from cluster and it will come to the input, right? The representation we say like this. One is your BIJ, from the bottom when you are getting up, that means I is your neuron, J is your cluster. That's why we are giving BIJ. But when you are coming back top to bottom again, we are giving the top up, down the weights. So this will be TJI. That means J is your cluster and I is your input. And this F2 layer is a competitive layer. That means the competition of the cluster will be going on in F2, that the input neuron is belonging to cluster 1 or cluster 2 or cluster 3 or cluster 4. They will be doing the competition, and finally the winning cluster will give that I am the winner, and the weight updation will be according to my you know, my condition. So this is about the gist of the ART architecture. So here I have given the just a diagram. This is in black color, so you must be understanding that. And anyway, I am just describing this. This is our new pattern. When the input is coming, this is our new pattern or the input. Here we do the categorization. What categorization? That is it the known cluster, or it is belonging to the any unknown cluster. That means whether it is belonging to the existing cluster or it doesn't belong to any existing cluster. Then you have to make the new cluster. So it is telling that categorization is it known, or is it unknown? And for doing this, you have to do these two process. One is your recognition, another is your comparison, right? First of all, you recognize, and after that you compare, and after that you determine that whether it is known, it belongs to known cluster or the unknown cluster. If it is a known cluster, then you give the winner node or the winner cluster, you adopt the winner cluster. And if it is an unknown cluster, then automatically you initialize that cluster again. That means node means, initialize node means another cluster you will form, and that will be the new cluster. So that is only we have taken here, that incoming pattern will be matched with stored cluster templates, right? If it is same or if it is close to the stored cluster templates, then automatically the weights will be adapted to the matching cluster, and if not, the new cluster will be initiated with the pattern. So this is your ART algorithm. So ART1, as I have told, that is there are two main ARTs, ART1 and ART2. Besides this, we have the ART3 incorporates the chemical transmitters to control the search process in hierarchical ART structure, and also ART map, fuzzy ART map, DART, distributed ART or distributed ART map, so Gaussian ART map. So these are the different types of ARTs which are available in case of the neural network. Now this is your basic structure. As I have told you, this is your F1, as I have told. Let me just change the color again because it is your white diagram. So this is your F1 layer. I have divided, first of all, I have told there are two layers. One is your F1, another is your F2 layer, right? Now here I have divided the layers into two parts. One is your F1A, another is your F1B. So what I am telling, that F1A is your input layer. Definitely here we are giving the input, that is your S1 to Sn. These are my inputs. After that we are interfacing. That means we are converting into a layer which are known as your X1 to Xn. Namely, generally this Xi is your same as your Si. That means whatever input you are giving, that will be same in your Xi. But it may be different. Between them you can make any function, and Xi may be some changed version of input also. That also can be given. Now from Xn, this layer F1B, there is a connection to the F2 layer which is my competitive layer. And there is a connection you can see, that will be the upper connection also. This is your upper connection, and this is your top down connection, as I have told, that bottom up weights and the top down weights, both of them will be there. So what is the actually functionality of ART1? This is about the ART1 only, because the binary mode we are telling. So we are giving that this is your input pattern, right? That is S1 to Sn. After that it will go to the input layer. This input layer is generally what I have told, that is your F1B, that is your interface layer, right? After that it will go to the output layer. Output layer is your F2, that is your competitive layer, right? This is your F2 layer. And here output layer, the winning cluster will be determined with some method, that which cluster it is winner. That means this input pattern belongs to which cluster, that will be the winner cluster, right? If it is same, if it can be found out, how it will be checked that it is the same cluster or this input pattern belongs to this cluster. It checks with these weights, that is your bottom up weights, but it is not sufficient. What it does, that after finding the cluster, again it will give the the output to the input layer with the top down weights, and again here also again we have found out the output, and the whatever output we are getting there, it should be same as your input. Then only we will say that this cluster is the winning cluster. That means only one side communication we will not do. We will go to the cluster, again from cluster to the input. Again, if we have find out that both these two are the same, then only we can say that it is the winning cluster. Otherwise we can just change it. So this is about the reset module. Here I have given them reset module is there. One is your reset, another is your grain control. I have told you there are 2 points we should take out. One is your vigilant test, another is your reset test, right? So reset module, they have the fixed connection weights. They implement the vigilance test, and excitatory connection from F1B and inhibitory connection from F1A. That means it is telling from the F1B, this is my F1B and this is my F1A. Excitatory connection from the F1B, that means here it will be plus, and the inhibitory connection from the F1A, that means here it will be minus. Similar case for the gain module also, excitatory connection from the input lines and inhibitory connection from the output layer. That means from the excitatory connection, that is output layer is your inhibitory, that means minus. From the input layer it will be plus, so that will be the excitatory connection, and this will be the inhibitory connection. There is a connections difference they are telling. So this is the algorithm, ART1 algorithm, but let me take the just 15 minutes or 20 minutes gap for this, for the tea break, and after the tea break again I'll continue for half an hour, right? And from 12 o'clock onwards we will start the optimization technique. 11:20 to 12 o'clock I'll just complete. I need half an hour time for completing my session. After that we will do the optimization technique 12 to 1 and 2 to 3, and from 3 onwards again we will do the MATLAB programming, right? Now let us take a gap for 15 minutes, then we will start again. Okay. Now let me start with the ART1 algorithm that we were at this point. So let me just elaborately say that what are the steps in ART1 algorithm. First of all, as we have seen earlier also, we have to initialize the parameter. So there are two parameters here. The scientist has given these two parameters. One is your L, another is your rho, another is your N. There are three parameters. So L should be greater than 1. What is L? L will be, it has been given by them that the bottom up approach will be, initiated or initial value of the bottom up approach will be L by L minus 1 plus N. That I will tell you. So this is the initialization of parameter. L must be greater than 1 and rho should be less than 1. Rho is your threshold. Now first of all we have to initialize the weights also. There are two weights I have told. One is your Bij and another is your Tji. Now for the first time Tji is equal to 1. That means all the T values top down weights value it will be 1. And Bij that is equal to, that it is telling that that should be less than equal to L by L minus 1 plus N. So this is be less than L by L minus 1 plus N and Tji equal to 1. That has been given by them only for the ART algorithm. Now it is saying that while stopping condition is false, that means when stopping condition is false, then you go for loop, right? Which loop? What do you want to do? It is telling that first of all you come to the initial position, that is your input. You have all the input vectors, as I have told you, that is your SI, all the input vectors. First of all you find the normalization of input, that is known as your norm of S. S means input. Norm of S means you do the summation of all S. Right? Norm of S means summation of all S. That means that is equal to summation of Si, whatever summation is there, right? And after that I have told that it will be finally, first of all there will be F1A and after that it will be F1B. There are two layers and I have told that F1B Xi generally it is same as your Si. So whatever Si we have got, that will be same as your in your Xi only. Now you go to F2. Now from F1, this is my F1, we are going to F2. Now which is the weight is connected with that? Bij. So it will be Bij will be connected with each and every weight. So what will be the Yj? Yj is your net, right? Yj will be the net. Now what will be the Yj? That will be the summation of Bij into Xi, right? Whatever Xi we have, since Si equal to Xi equal to Si, so Xi will be in the F1B layer, there will be X1, X2 or Xi. So Xi into Bij and the summation of these two will be the final net, that is your Yj. Again it will be in the loop if the reset is true, right? If reset is false, then it will come out of the loop. Now we have to do the winning neuron or the winning cluster. We have so many clusters in the F2 layer. Now each and every for each and every cluster we have to find out the net, and finally we have to check that for what j this Yj is your minimum. Just like that we have pointed in vector quantization, we have done in SOM. Similarly we have to do in ART also. So the method is different. Here we are giving the output Yj we are finding out, and finally we are saying that for what j this Yj is your minimum. When we have found out the minimum j or minimum Yj, that means that jth cluster is the winning cluster for us, right? Similar we have done in vector quantization also. Now here what is the difference? When we have found out the cluster, that is your Cj or what Yj is your minimum value for this, in SOM or in case of vector quantization it was the final step, right? When we have found out, so that cluster we have taken. But here they are telling again the second step you will do just for comparison purposes. This you have recognized. Now you will do the comparison or the matching. Really it is for that or not. Now again what we will do, we will come down. We have reached here, right? Now we have reached here, now we are coming down. What we are doing, recomputation the activation of X for F1B. So we are doing TJI into SI, right? Whatever SI we have inputted, that should be, it will be coming down as TJI into SI. SI is your input. And finally we have to do this is your X, that means we are finding out again input and finding out the norm of X, that is your summation of the X. That means we have, first of all, we have found pele SI. After that it has gone to the F1B layer, where we are telling that Xi is the same as your SI. So we are going up. Here we have found out the Yj with the Bij with Xi and Bij. We have found out the winning neuron or the winning cluster, and after that we are again coming down, and again we are finding Xi again with this formula, that is Xi is equal to Si into Tji, right? And when we have found out the Xi, then this Xi and the input Si, that we are checking. If it is less than threshold, that means if it is your error controls is there, then you just omit this. And if it is greater than this, then you update. That means what is the update formula? That means update the weights. That is your Bij equal to this and Tji equal to this. This is the formula. According to the formula, whatever it will be done, then you can just calculate that what will be the Bij and what will be the Tji, and again the loop will go on. So this is your ART1 algorithm. There are two layers, input and the competitive layer. So if you want to find out, let me just tell you that what is the vigilance threshold, right? There is a term, that is your vigilance threshold. Now vigilance threshold sets the granularity of clustering. That means how much big will be your cluster, how many neurons will be in one cluster. So that should be your main target of research. That is threshold. Which value of threshold you should take? It may be low, it may be high, it may be optimum. So for the low threshold, large mismatch accepted, but for the high threshold, small mismatch is accepted, right? Many small clusters, higher precision. Here it is a lesser precision. That means what? That if the row is large, then the cluster number will be, this is your large number of clusters. It is white in color, so it is not finding. Let me take the color red. Right? For the large row, what it will be the case? There will be a large number of clusters is there. For the small row, it is not precise. That means that there will be the, the cluster will be less. That means all the neurons will be tied to the one cluster only. That means the clustering will not be accurate. So if it is higher threshold, then the precision will be more, and if it is the low threshold, then precision will be less, right? So this is actually the vigilance threshold that you have to take care of. And this I have told you that after the, you find out that it is greater than X by S is greater than rho, then you have to adapt the weight, or you have to change the weight. That I have given you already, the weight updation. Tji will be same as your Xi only, and Bij will be L into Xi divided by L minus 1 plus the norm of X. This is your norm of X, that is a summation of X, right? This is your summation of X, this is the norm of X. So that will be the updated value of the Bij. That is a bottom up approach. Now if I take one example that you can just write it down, then you can just do it. Just 1 minute. So let me write the problem first. Let me insert one blank slide. So let me insert the blank slide here. I will just write that the equation or the values, you can just note it down and you can just do it. So it says that consider the ART1 network with F1 layer and the F2 layer with the bottom up weights and the top down weights. So Bij, it is given as, so we are writing that Bij, it is a matrix, right? Half and 1 by 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. Half, 0, half, 0, then half, and in this side all the values are 1 by 5. 8 values, 1, 2, 3, 4, 5, 6, 9 values, right? There are 9 values. That is your Bij. All are, these are 1 by 5, and this is half 0, half 0, half 0, like this. And the top down approach, it has been given as the matrix, that is your 1, 0, 1, 0, 1, 0, 1, 0, 1. And these are all ones. One zero one zero one zero 101, and all the values in the lower row, that will be equal to 1. And the input, what is the input pattern that I am giving you here? The input pattern, that is your SI, is given as 1 1 1 1 0 1 1 1 1. There are 9 values. Vigilance parameter, that has been given as 0.4, right? First time it is the vigilance parameter, it is given as the 0.4. Now some values will be assigned to you, right? Some values I am giving you for the calculation. One value is your n. You need n. N equal to is your 9, right? Now L also you want. L is equal to is your 2, and rho, that is your vigilance parameter or threshold, vigilance threshold, that is equal to 0.4, right? M abhi nahi chahiye. So rho is equal to 0.4, n is equal to 1, and L is equal to 2. These are the 3 values. Now according to the your algorithm, now what you have to do, first of all, what you have to calculate, Bij, right? We have to first calculate, that is your S equal to summation of Si, right? And send input signal as into the F1A to F1B, that is Xi will be same as your Si, and after that you have to calculate Yj equal to Bij into Xi. Now we have Xi, we have the Bij. Bij is also given to us, right? Bij we don't have to now calculate. Finally when we will do the updated Bij, that time L or N will require. Now we have Bij and we have the Xi. So here you can find out the Yj, right? Bij into Xi, that will be your finally Yj. So for Yj you can find out first of all. First step is your summation of Si. That we have found out. Summation of Si. And what is your Si? Si is the input. This is your S. 1 plus 1 plus 1 plus 1, 4. Plus 1 plus 1 plus 1 plus 1. That means total Si is equal to 8. Is it so? This is your S. Second point, what it says? That Xi equal to Si. That means what will be your X? X also same as your Si, that is your 1, 1, 1, 1, 0, 1, 1, 1, 1. So this is your X. These two steps we have done already. So these are the two steps. One is your S, another is your X. Right? These two steps we have done. And finally we have to do the Yj. This we have to calculate Yj. Right? You have the Bij and you have the Xi. So you can find out the Yj also. Right? Both the terms are there with you. So you can find out the Yj. Now what will be your Yj? So Yj will be the matrix. So you have to find out Y1, Y2, Y3 and Y4. Similarly for Y8. For the 8 points you have to calculate the the Y matrix. After that you have to find out that which one will be giving you the minimum value, and that will be the winning neuron, right? And after that again you come back to the initial part. Again you calculate Tji. This is your Tji. Tji into Xi again. Then you have to match that whatever is your Si, that was your 8. And finally you have to calculate what will be your X, and then this divided by this will be calculating as a less than rho or the greater than rho. And rho you have, that is your 0.4, and if it is greater than rho, then only you have to update. If it is less than rho, then you have to just omit it. So this is your ART1 algorithm, and you can write the MATLAB programming also for this ART1 algorithm. Right? For each and every clustering method you can write. K-means clustering also somewhere it is related to this. Naive Bayes classifier also, that also somewhere related to this. All the classifiers or all the clustering methods are generally do the same algorithm only. Right? So these are the three clustering algorithms what we have done today. One is your vector quantization, another is your Cohen self-organizing map, and third one is your ART, that is your adaptive resonance theory. Now after 5-10 minutes, because we need the 5 minutes that to connect the laptop of my students. So these 3 students are working on the optimization algorithm. So these 3 optimization algorithm, they will be telling you that what are the functioning of the optimization and how actually they will be using with the image processing. So they will be just entering, they will not show you the implementation, but they will just tell that how the image processing and the optimization algorithm can be matched, right? So we'll need just 5 minutes to tune their laptop. After that we will go one by one. So before lunch we will be only PSO, and after lunch we will do the BAT algorithm and BFO, that is your bacteria foraging optimization. Right? Just give us just 5 minutes. Yes. वो कपिला जी से लेके आए होंगे. अच्छा, ओके. ये चाहिए होगा इनको. तो गिरेगी नहीं, मैं हूँ इधर. ये गिर गया, लग जाएगा. अच्छा, मूवमेंट के साथ में होंगी.
उसको मैंने होल्ड पे किया. कौन सा? को इनवाइट किया सुनने के लिए. हाँ जी मैम, अभी इनवाइट किया. सर ये फिक्स तो हो जाएगा ना, इसके नीचे नहीं जाएगा। हाँ जी मैम।
इसको थोड़ा सा बाहर ही करो।
मैम ये डेंजरस है।
सर इसके आगे रखने के लिए कुछ सपोर्ट नहीं होगी? कुछ सपोर्ट रख दें अगर इसके आगे।
नहीं, ऐसा करो, इसको आगे दो।
नहीं मैम फिर पीछे ईंट तो नहीं पड़ी होगी कहीं, मैं लेके आती हूँ।
पीछे थोड़ी जाएगी तो सामने।
मोreover मैम इनका तो वेट भी इतना नहीं है।
मैं खड़े होके देखती हूँ।
सामने कर।
एक बार खड़े होके देखती हूँ कहाँ तक जाता है। सच में गिरेगा।
हेलो हेलो, नहीं शायद उन्होंने नहीं सुना। हेलो हेलो, नहीं हेलो।
Hello, yes.
Yes, Matri ma'am, may we have doubts till that they are connecting all that?
हाँ बोलिए बोलिए।
Ma'am, you have told us that compute the Euclidean distance between the input and the output neuron, was input neuron and the weights.
Cluster, yes.
Cluster quantization.
Hmm.
Yes, ma'am. Ma'am, in that question, there were two neurons having the same Euclidean distance. And maybe both are minimum. In that case, how will approach for that?
Anyone you can take.
Anyone.
Anyone, but generally concept wise the first cluster, whatever it will be the first cluster, then only we can consider this. But in case of ART also you can get such type of situation. The problem I have given, in the first instance only you will get this situation, you will get the minimum same value, that is your 1 1 1 1.
Yes,
every distance will be 1. That time you have to take only first one as your winning neuron.
Okay.
Right? Or otherwise you can take the other one also, there is nothing problem is that, but conceptually it is taking that first neuron, first cluster will be as a winning neuron.
Okay, ma'am. And the ma'am second doubt is like many times we are computing the Euclidean distance. And Malanopes distance is also one of the popular distance which is being used nowadays. So where we are supposed to use Euclidean and where Malanopes, or there is no difference?
Difference is there. I will not say difference is not there. Euclidean distance is basically, that is taken as a best because for statistical analysis also, everywhere, wherever we do the statistical testing, for example, chi-square test or some other testing, in statistical testing also we take the Euclidean distance as your one parameter or objective parameter, standard parameter we take. That's why we are doing here the Euclidean distance as a standard parameter. Otherwise, except the Euclidean also you can take the other parameters, but in vector quantization and its Cohen sum, they have told that only Euclidean distance only to be considered to calculate the winning neuron, no other distance. But in case of networking, for example, when we do the networking or some networking environment, either in wired or wireless, something distance if you want to find out, you can take the Euclidean distance or other distance also, but not in neural network. It has been developed that researchers have told that in case of clustering, the Euclidean distance gives us the best result.
Okay. And ma'am, one more question is like in nowadays we are moving from static to dynamic world. So neural networks are also capable to capture the temporal analysis of any like image or speech or anything. So
Yes.
what type of neural network should be suitable for that?
This ART network only we do the for the online capturing or the online clustering. The vector quantization and the SOM method is used for offline, but ART we can use for online clustering method.
Including the temporal behavior of the image or the signal.
Not image. I am not going about the image. I am telling that if you do the online clustering, that means the running procedure at the runtime only you do the clustering. That time this ART method will be the best. But in case of the online image processing, it may be different. It may be the other clustering method, because image capturing and then online, if you want to do the clustering at that time, so that means you have to take care of both that means image capturing also should be your temporal, and correspondingly cluster information also should be temporal. That time you have to see that which are the methods you can use.
No, ma'am. My question is not this, like whether I can use this in real time or not. My question is whether these networks are capable of capturing the temporal behavior of the input pattern.
Yes,
Like
of
my
course.
pattern
Acha, input pattern. Okay.
Yeah.
I was just thinking that real-time application or the something online application.
No.
So in case of the neurons, whatever the ART method or the SOM method, both these methods are capable of taking the temporal information of the neurons.
Okay.
Both
So
ART1, ART2, then SOM, both these three are capable of taking the temporal information of the neurons also.
okay. Thank you so much, ma'am.
Okay.
Yes, hello, ma'am.
Hello.
Hello.
Yes.
Yes, ma'am, there is a question.
Sure.
Regarding this, that when we go from the F1B layer to the upper one layer, right? That is a competitive layer. We made the calculated the winner and all. Then when we come down from while calculating TJI into SI, means while coming down, so we'll be taking the step only for the winner.
I'm not getting what you are telling, that when we are coming down, yes. Yes. Only we are taking for the winner cluster only.
Means once we have calculated winner cluster, then
Yes.
the TJ into that thing that has to be calculated only for the winner.
Only for the winner,
Only
yes.
for
Yes. Only for the winner. And after that
But
only, we will calculate Xi again with that winning cluster, and we will check that whether Xi what we have got from the top down and your SI and the SI which we have inputted, both these are same or not.
means TJI into YJ should be equal to SI.
Xi, yes. SI, yes.
SI and XI so summation
It should be same. It should be same, but generally we don't get same. So that's why we have taken the threshold row.
Threshold, the row.
Yeah.
Vigilance.
Vigilance.
Right.
Yes, vigilance threshold. Yes.
Okay. Now, ma'am, please, would you just explain this thing, that the loop, you have drawn this block diagram, which is explaining Art1 algorithm, which is showing this excitatory and inhibitory signals, gain control mechanism and reset mechanism. Right, ma'am? So now see, from TJI into that YJ, we have come down to XI, and then we have compared it with the thresholds, and then if it lies within the threshold, then where to go?
If it is less than threshold, then you have to reject it. You have to just reject it.
Okay.
And after that, if it is greater than threshold, then only if you have to the weight updation and you go for again loop. That means what? If it is less than threshold, then you come out of the loop. That means you have got the winning neuron, right? That is same. Matlab, the cluster you have found out. But if it is greater than rho, that means you have not found out the actual cluster. You have to do the updation, and again you have to do the the loop, and again you have to find out the winning neuron or winning cluster. Again you have to do the calculation.
No, ma'am. Then what is this? That gain control and reset वाला जो loop है वो कैसे आएगा function में?
हाँ, वो फिर से ऊपर आ जाएगा ना.
First of all, gain control mechanism. Yes.
Gain control is your just that is giving the excitatory or the inhibitory function to the top layer or into the from the F1B layer. It is giving the inhibitory connection from F2 to gain control and excitatory connection from F1B to the gain control. This is for just your control the parameter, gain parameter. This is nothing with any loop. Loop is basically controlled by the vigilance threshold. If it is less than threshold, then it will come out of the loop. If it is greater than threshold, then it will go to the loop, but with the updated weight. That is the basically condition.
That means if we are rejecting it, so that means we have to go into the loop. We have to go into the loop, and again we have to with the updated weights we have to again calculate the new winning cluster.
New winning cluster, again you have to check it. If the new winning cluster again it is same with the input, then you come out of the loop, or otherwise you come out of the loop means that you check for another neuron, another input pattern. Or otherwise, if you have not come out to come up with that actual winning neuron, it doesn't belong to the winning neuron, or if it is greater than threshold, that means it is not the correct cluster. Then again you update, and then again you go for the loop.
And then that means this reset mechanism is only for that if you want to go out, come out of the loop.
Yes. Yes. If the reset is true, then only you go. Otherwise, if it is false, then you come out.
Okay. Thank you so much, ma'am. And then yes, there is one more, ma'am.
Yes.
That is that the Euclidean distance. That in vector quantization you have said it is with the square in strong Euclidean distance, but matter that means squared will be less only na, or means for calculating the Euclidean distance.
Actually, there is no difference in that. If you can take the squared also, or you can take out simple Euclidean distance also. But it depends on the scientist that it has given that you don't have to find out the square root actual Euclidean distance. You find out up to squared value only, and from squared value also you can calculate. This is the development, First of all, there was a vector quantization. They had given that Euclidean distance. Second researcher or second scientist has told that you don't have to find out the Euclidean distance. If you find out the squared Euclidean distance, then also it will go up.
That will also serve the same purpose.
Serve the same purpose. So depending on the different algorithms, so we have found out this thing.
And then, ma'am, there was one more question that in the first that block diagram where the categorization known and unknown, then once it is known, then that you will adapt. But once it is unknown, but once it is unknown, then how to take the cluster means the center of the cluster. What will be the center means? How will define it?
Here there will be no center of the cluster. So in vector quantization, we find out the cluster. Here, what we in ART, what we do, the ART or something SOM in ART, right? In ART, we don't find out the cluster center or something. we do it that if it is known cluster, then it's okay. Otherwise, if it is not known, then you define the another cluster with those neurons, input neuron. That means it is a different cluster. But we don't find out the centroid or the center, or we don't find out the Euclidean distance. You have found out in ART we don't find the Euclidean distance.
Yeah, but ma'am,
So there is
then
no center is required in that.
no, but in the second layer, in the ART, in the upper one layer, we define which is the competitive layer, the F2 layer. So those neurons are the cluster basically, 1, 2, 3, 4.
These are the clusters, but
Yeah.
what we define, we don't find out the cluster center. We are defining the clusters with the help of the weights, bottom up weights and the top down weights. So when
Yeah.
we find out the new cluster, then we define the updated weights. That means what will be the updated weights of that cluster, bottom up weights and the top down weight. That's all. We don't find out the center.
So that means that will be the new neuron added to the output layer, to the second layer,
Yeah. Yeah. And with the new weights
with
added,
new weights.
with new cluster with the new weights of the BJI and the TJI.
But how those BJI and TJI will be decided? Just
That
like
will be
initialization?
no.
Just like
That will be the same as your beforehand, no? That we have calculated the BJI and the TJI, that you have already have this, with the matrix that L minus 1, that you have, I have given you the formula. Right. Anyway,
nine, then it will
anyway, we
become
will
10.
continue. We will continue in the, after 3:30, we can just continue that. Now, let me just welcome Jagriti. She is the student of mine, and she will be telling you particle swarm optimization. Ma'am, आपका question मैं बाद में कर दूंगी 3 साढ़े 3 बजे. Then again we will discuss, right?
ठीक है, no problem. Okay.
Okay. Okay. Okay.
My name is Jagriti Sani, and now I'm going to taking the session for particle swarm optimization. The content that I'm going to cover in this topic is related to origin of this optimization technique, concepts related to PSO, such as variable initialization and some topologies related to neighborhood, algorithm for PSO, and some MATLAB-based implementations that can be used for different applications. So let us start with particle swarm optimization. What is actually particle swarm optimization? We are doing some population-based stochastic optimization techniques. It deals with a group of random variables, and all those variables are defined in some predefined patterns, and we don't know actually the behavior of those particles. We are working for a flock of birds that is continuously moving in some direction, and we have decided some pattern for them. We are estimating some values for them, and then some analysis are performed accordingly. This algorithm was first developed by Dr. Eberhardt and Dr. Kennedy, and in 1995. And it was actually inspired from the social behavior of bird flocking or fish schooling. Presently, we are going to discuss the bird flocking behavior because it is most suitable to discuss the particle swarm optimization. PSO till now has been applied to so many areas such as function optimization, artificial neural networks, fuzzy system control, and some other areas wherever GA can be applied. You might have heard about GA, that is genetic algorithm, in which we mostly consider the genetic behavior of particles. They are transferred from parent to their child, and continuously they proceed for some optimization algorithms. But in this case, we are working on a group of particles. We are not considering single or two particles. We have just initialized a population, and all the optimizations are going on those population-based initializations. First of all, the origin of particle swarm optimization. This technique is inspired from the natural social behavior as well as the dynamic movements with communication of insects and birds. As human beings used to share their ideas, their experience, and their behavior, in the similar manner, birds have some techniques to share their experiences. They usually talk to each other and share the information about food, their inhabitants, and some other related information. So the same behavior is utilized for some analysis over some applications. Here, what we are considering is some dynamic movements of birds. They are moving in certain directions. In most of the cases, we consider the food particles for which they are going on search. A group of birds in the early morning, you might have seen so many birds, they go for food search in early morning and they come back with some food sources for their other group members. They usually move from their inhabitants and then start structuring in some formats. As shown in first figure, the birds are collaborating towards some particular pattern, and finally when they start observing the food source, they come more closer to the food source, they start forming a much optimized pattern, and they start following a particular sequence to reach that food source so that they can reach up to that food source in least time and they can get maximum output from that source. Here is a particular sequence that those birds are going to follow, and this sequence is here utilized in various applications for optimization. Let us imagine a flock of birds that is circling over a space and they are just smelling a source of food. All of them want to catch that food source. The one who is closest to the food chirps the loudest and the other birds swing around in his direction. It is the pattern of communication. They are sharing their thoughts. If any one of them is getting the idea that food source is in this particular direction, he starts chirping louder and he is sharing some information that I have got an idea about food source, and others starts following him. For the next step, if any of the other circling birds come closer to that target, then the first, as compared to first, the second one who is going to get the food source much nearer to him, he starts chirping much louder as compared to the previous one. So the complete bird formation, they start noticing that bird now. They, all of them share the information that some other bird is going much closer to the food source, so they have to form other pattern to follow that bird. Each bird is sharing their information in the similar manner, and it becomes a optimizable solution for them, because if a single bird is going for a food search, he will have to spend more hours to search a single food source. But if they are working in a group and sharing their information, their experiences, they are knowing that in this direction food can be searched in best possible manner, so they are sharing their ideas and trying to optimize their solution to search that particular food. And in this pattern, the tightening goes on, and finally they reach up to the food source. In the similar manner, the activities of birds is processed on PSO, that is particle swarm optimization. Swarm means we are working on a group of birds or group of insects, and we are studying their behavior. Now PSO follows some iterations. As earlier I have told that birds are continuously sharing their information, and every time a bird comes closer to the food source, the other bird starts following him. In the similar manner, for the optimization, we are considering some particles, and those particles are doing some iterations. In every iteration, they are going much closer to the food source. Whatever we have given them a target, we have assigned them certain target that they have to achieve this one. In case of birds, it is a food source, and in case of particle, when we have to move certain application, they have a target, and they every time they are doing iterations to get that target. A group of variables have their values adjusted closer to the member whose value is closest to the target at any given moment. Every time iteration is following the particular situation, for that the particles are having best and closest value to their target. All of them are sharing, and there will be a comparative analysis that which particle have best information, so that other can follow that one particle. What is the actual process going on behind PSO? In PSO, each single solution is a bird in the search space. We are just relating our swarm techniques with the particle movements. Insect of birds is going to be related with the particle movements. So what we call them a particle. The birds are now related with the particle. All particles have their fitness value, which are evaluated by the fitness function to be optimized, for which we are working, and have velocities which direct the flying of the particles. Now again, we are trying to relate it with the movements of bird. All the birds have their own abilities to search the food source. In the similar manner, particles have their specified fitness functions to search their optimized targets. In which direction they have to move, they have some estimated values for that, and they have to move to that particular direction. Here again, we are assigning some predefined attributes to those particles. They can be velocities or their positions. For example, if a bird is starting his journey from his nest, then it will be his current position, and then he start moving toward the food source, and his current location will be updated all the time. Normally, as we use our mobile phones, our current locations are updated all the time. The similar manner, we are using some optimization technique here, that the location of particle will be updated all the time, and we are sharing the information accordingly, that so that the closest solution can be found. The particles fly through the problem space. Whatever we have given them an assignment, they are working on that particular problem space, and every time they update their optimum values. Here I am showing a graph with certain group of particles, so that we can just analyze how these particles are moving in certain space. First of all, we have to initialize a group of particle. As shown in this diagram, you can see that we are having a single particle first. This particle is showing its behavior in blue lines. In these blue lines, they are not more considered because we are not working for a single particle. We are working for a group of particle. So these are of least importance. The single particle is of least importance. It can be considered in case of GA, because there we have to move according to genetic behavior of that particle. Now we are moving toward the group. For the very first time, we are going to initialize 5 particles. You can see the red part that is showing the movement of 5 particles. Now let us consider a situation if 5 experts are sharing their information. 5 members are sitting in a room, and they have to solve certain critical problem. In that case, they are sharing their information. But if 5 members are there, they have limited information and they can share limited solutions over there. But if we have more number of experts over a certain area, they can share more information and we can calculate much optimized solution. In the similar manner, the graph is showing in case of red, where we have initialized 5 particles, you will see there is much heavier response. The particles are showing more moments and they are just simply trying to get the optimized solution, but it is much difficult for them. But in second case, when we have decided 50 particles, the response is shown by yellow color. It shows that the behavior of particles goes much smoother as compared to the 5 particle, because they are able to share more ideas and they have more experience to get the right solutions. But in third case, we have initialized 500 particles. Every time we are just initializing a population for that particular search space on which we are working. Now we have decided 500 particle and the response is shown by green color. Here we can see much smoother response. It is going much optimized in a much optimized way. Even you can see some little spikes in between, but still as compared to the other groups, it is much better in this case. So accordingly, all the particles, if we have initialized a group of 500 or 1000 particles, they are sharing information so that a much smoother response can be observed for the particular optimization. Now we have 3 major solutions in this case for particle swarm optimization. We are working on 3 values. The first one is best solution it has achieved so far. We are working for a single particle in this case. We have decided a group of particle and out of that group we are considering one particle and we are considering his properties, his particular properties. We have assigned certain best solution to that particular particle. For example, first of all, we calculate his position. His current position is assigned somewhere in the search space, and second, his velocity, how much movement he is going to take in that particular search space, and it will depend upon his experience. So the first value that is assigned to an individual particle, it is told as present best and denoted by P best value. The second case, we have best solution obtained so far by any particle in the population. Now we are shifting our concentration toward the population. The group of particle is working for particular optimization as we have considered the P best value, present best value. But now all those present best values are combined to get a global solution. All those present best values will be compared and the one particle which is having much closer results, much optimized result, will be assigned as a global best particle and his value will be represented as G best value. The third case, we are having local best values. Best values of particles arranged in topological order. In first 2 cases, we have just assigned a search space to all the particles and all of them are moving in that particular search space. But now what we have done some topological order for those particles. We have assigned certain definite location to those particles. For example, if we take this type of search space and we are just going to assign this position to such particles. We have assigned particular local area to all particles and for example 5 to 10 particles are assigned to that particular group. In this case, they will be assigned local best values. As shown in these positions, they will have certain local values and these local values will be compared to get the optimized solution. It makes our research, our optimization much appropriate because they are able to share their information on localized basis. They have defined certain area on which they are working. Now the algorithm is going to keep track of 3 basic things: the target value or the condition. For example, when we were considering the swarms or the working of birds, we have targeted a food source to them. They were working for that food source. In case of particle, we have assigned some application specific value to those particle and that target will be their optimized solution for which they are going to work during the complete iteration process or optimization process. The second is global best value, as we have discussed earlier, that indicate particle data that is closest to the target. At particular instant, we are measuring the global best values so that the whole group of birds can move to a much optimized solution. And the third is stopping value. There can be certain critical applications where we are not able to match the target value with specified parameters. In that case, we need to change our parameters. So in our programs, whatever we are doing for PSO optimization, we have to specify a time limit or certain other criteria that our optimization must stop at this value if a target is not found so far, so that some other parameters can be assigned to those particles, and this again start iteration on those bases. The second thing, each particle consists of data representing a possible solution that we were considering first, the p-best solutions. Each individual data is going to have that one. The velocity value indicating how much the data can be changed. We are taking the velocity parameter here. So a velocity parameter will be assigned to each particle for his particular movement, and the p-best value indicating the closest the particle's data has ever come to the target. इससे ये पता चलेगा कि टारगेट के कितना क्लोजर एक पर्टिकुलर वैल्यू एक टाइम पे आ सकती है, और उसकी हम ऑप्टिमाइज कर रहे हैं बाकियों के साथ कंपेयर करके, सो दैट वी कैन get a better solution on the comparative basis also. Now we are going to discuss the concept of neighborhood. Till now we were assigning a particular space for all the particles, but now we are going to work on the neighborhood technology. As we have discussed the local best values earlier, the local best values are used in this neighborhood concept. Now it is so common to see PSO algorithms using population technologies or neighborhoods, which can be smaller, localized subsets of global best values. What we are saying is, we are using this particular search space and we have assigned these local values to a few group of particles. We have decided we have separated our search space according to this figure. And now we are going to decide a neighborhood for all the particles. For example, we have initialized 500 particles earlier in our program, and those 500 particles will be assigned some area now here. For example, the first one, here we have assigned 100 particles. For the second one, we have assigned 50 particles. In the similar manner, a topology will be fixed for all the particles, and they will be moving in their particular search space now, the particular area defined for them. These neighborhoods can involve 2 or more particles. As I have told you, if we are working on a smaller range of particle, we are going to assign 2 or 4 particles in particular area. For example, if we are working on larger size applications, we have more particles in initialization. In that case, we can define more particles to particular search space, which are predetermined to act together, or subsets of the search space that particles happen into during testing. All those particles are divided into certain subsets. Whatever we have assigned in these areas, we are calling them subsets, so that they are always working in particular group. And all these subsets are going to share their information in final iteration when we have to do the final comparison for the threshold levels. Every time they are doing iteration in their own local search space, and whenever we are going to find the optimized solution, we are going to compare their values, and the final global best value will be assigned for that particular application. The use of neighborhoods often help the algorithm to avoid getting stuck in local minima, because if we have this search space and all the particles are working on this area, they are moving in the complete search space, they will take more time for getting optimized solution. But if a group of particle is working in different location, and they are again updating their values, and finally we are just correlating their values and getting the compared solution, it will be much easier to us to get the optimized solution, and it will reduce our time taken for the complete optimization. Here I am just showing some topological techniques that we usually follow for PSO optimization. The first one is single-sighted, where individual only compare themselves to the next best solution. We have just shown it by first figure. Sorry, I just need to change. It will be more visible now. In the first case, we are using this part, the single-sighted. All the particles are moving in a particular direction. This type of topologies can be used in pathfinding applications. PSOs are also used in some pathfinding applications. Here, this type of topology is mostly considered. The second case is ring topology. Here, all the particles are working according to their left-based and right-based solutions. They are sharing their information only with the left-based particle and right-based particles. So it is shown by this formation. It is commonly used in computer networking. We have already studied. Most of you might be aware of the topologies in computer networks also. The similar manner, we have assigned particles in such space. They are just sharing their information in some topological order. The third one is fully connected, as shown by this figure. In fully connected topology, all the particles are sharing their information to each other, but we have decided some parameter for this decision, so that they have to share only the specified information. They will not waste time to share the complete information. We have assigned some targets to each topology. And the last one, it is completely isolated. As I have earlier discussed, if we are having this search space, we are just assigning these areas to these particles, and these groups are going to work for these particular areas. We are just going to assign them particular area, and they will be all the time optimizing values for that particular area. And finally, all of these will be compared to get the best solution for that particular application. Till now, we were just discussing the behavior on the basis of birds. Now we are just going to the implementation part. How the first case, as shown in figure, we were just related with the birds, and now we are just moving to particle behavior, how particle can be actually implemented in particular application. So the concept of PSO implementation just take care of these values. Each particle changes its position according to its own experience and experience collected from the neighboring particles. In earlier example, we were using the experience of birds. All the birds were sharing their experience. Now here, the particles are going to share their experiences. All the particles are having some parameters, and their parameters will be discussed among them according to each optimization. For example, we are working on position, if we are working on velocity, or if we are working for intensity level variations, accordingly the information will be shared by all particles. They are just trying to move towards the best solution. The performance of each particle is measured using a fitness function, which is application dependent. For implementation of PSO technique, we just have to decide a fitness function, and it will be the target for all the particles. This fitness function will decide their behavior and their movement, in which direction they have to move and how they have to get their optimization results. Second, we consider two major parameters for the calculation: particle velocity and application and position. It will even depend on certain applications also. In our case, wherever we are working for our thesis work, we are just considering these two values, particle velocity and position, and some other parameters will also depend on application. Both of these are updated after each iteration, and solution moves ahead towards the best possible results. And all the variations are done in order to achieve desired intensity value throughout the image. In case we are working on certain image, PSOs are generally implemented for image kind of applications, and here we have to, for example, make some intensity level variations with the help of PSO. In that case, we have to assign some intensity based parameters to those particles, and they will be moving their all the iterations according to that parameter. Here I am showing just some mathematical function that will be useful to define the algorithm for optimization of PSO. We utilize a root mean square error function as a fitness function. It is just a specific application where we can just utilize our root mean square value to assign some parameters to all our particles. The root mean square values is shown here. We are denoting it by RMSE. The M and N shows the dimension of our particular image on which we are working. For example, if this is image, the M into N size is taken because we are just usually implementing these codes in MATLAB, and it works with matrix analysis. So we are just assigning M cross N values to our optimization. The next is F cap and F. Here the F shows the true image, and the F cap shows the restored image. We just have to make the comparison on both of these so that optimized solution can be achieved. We are having certain parameters, those will be compared to get the optimized solution, and this complete process will go on our m into n size image. Now this m into n size image is going to act like a search space for those particles, and they have to work on this particular area. The other mathematical function for PSO implementation is as shown by this equation, the equation for V. In case if we are working for velocity level variations, the present particle position, present x, and velocity v of each particle will be updated with each iteration. Particles are doing continuously their iterations to achieve best solution, and their values will be updated after each iteration. We will just go define a program for that, and the iteration will be moved to optimize the solution. As shown by this equation, the present value will be updated as per the current value of x as well as its velocity, so that the complete search space can be covered with this optimization. The above one shows a formula where we are considering the parameters random, the p best values, and the present best values, and here are some constants that are used in the form of weighing functions. We are just assigning some weights to all the particles for their moments. All these parameters can be utilized, and in case of certain applications we just need to drop some of these parameters because all of them are not utilized in all applications. It is all dependent upon our target. Whatever we have to achieve, we have to define parameters accordingly. Next, I'm just discussing the pseudocode for the optimization procedure. First of all, we have to initialize particle population. As we are working on a group of particle, we have to make some estimation for how much particle will be initialized at initial level. We are making a population type initialization, and second time we are just working for estimation of intensity of particles as an objective function. In our case, we have taken the intensity as a target. We have to improve the intensity based values. So next, what we are going to do, every time we will calculate the fitness value of particular particle. First of all, in first iteration, we will just check the fitness value of individual particle, and then it will be updated to the global best level. So first we are just going to, if values are better in case of present, then current fitness function will be updated to the p best level. At the current position, whatever the value a particular particle is having, if it is much better than its previous value, it will be updated as a p best value. And in second case, we are just going to update the global best value, and it will be assigned by comparison of individual particle properties, and the one which is having best property will be updated as global best particle, and all the particles are going to follow his position. For each particle, we have to calculate velocity. In case of image processing, we are just considering the parameter velocity. Some other researchers can take other examples also. They can take other parameters for initialization also. And every time we have to update that v value as it was discussed in this formula. Whatever the parameters are initialized by the programmer, he is going to define those parameters in his pseudocode, the MATLAB based code, and every time those particle values will be updated. And finally, the position of particle will be updated to get the present best value. Now, if we compare it with our SWAM positioning, the SWAMs were working toward a food source. All of them were moving toward a best food source. In this case, again, particles are moving towards their target. For example, if they have to restore certain kind of image, if they have to work on enhancement of certain image, then in that case, they are just going to update their values. In that case, the SWAMs were updating their position for the best food arrangement, and in this case, they have to update particle values as per the optimized solution of that particular application. And finally, we will get the best solution for that particular application area, and all the particles will be updated to that particular best solution. Now, it is just an example algorithm for PSO optimization. It is application specific again. People can initialize their own algorithms depending upon what kind of parameters they are initializing and on for what kind of application they are going to use their PSO technique. First of all, what we are going to do is we are just going to initialize our population. As I have discussed earlier, we have to initialize certain particles, for example 500,000 particles, whatever our search space requires. For the next time, what we are doing is we are doing intensity based estimation. In our case, we have taken intensity as major parameter and we are considering it as a fitness function for those particles. All time, those particles are going to update their values for that particular intensity function. Then we are going to initialize our secondary parameters. Those are particle velocity and positions. The iterations will be updated according to these values. Every time the particle velocity and position will be checked, and if it have its position and velocity better than the previous, it will be updated as present best solution. And finally, all the particles will be compared for their present best values based on their position as well as velocity, and the global solution will be calculated. Next, as we have discussed earlier, the RMSE that is assigned as a fitness function, it will be assigned certain threshold level. Now whenever we have to implement certain kind of optimization technique, we first of all we do certain kind of estimations so that certain rules can be defined for the optimized solution. We have to do certain estimations prior to implementing our original algorithm, and here we are deciding the threshold value according to those preset values, those estimates that various researchers have calculated. If someone is working on PSO implementation technique, he can refer to so many research papers. He will just get the idea for the threshold value estimations. People might have done some analysis on images by implementing some filters, etc. If they have to enhance the resolution level of certain images, they will have some threshold values for that, and every time they will be estimating some values, some parameters for that. Here again, we are setting some threshold level to this RMSE, and in case in our first iteration, if that threshold value is matched and our RMSE is exceeding above that threshold value, we need not to work on other procedures, whatever we have defined in an algorithm, because we are just getting the optimized results in first iteration. But these are very rare cases that we are going to get our result in first iteration. We have to do even 50,000, even hundreds of iterations are working continuously in basis of microseconds or seconds. They are continuously updating their values. For the case when our threshold level is not matched, it is not matched, that time we have to evaluate the fitness function of each particle. Now we are going to individual particle level. We are just checking the fitness function of that particular particle at certain current position. If its value is much better than this earlier value, whatever it was assigned in the past iteration, if present value is better than that, the fitness function of that particular particle, that individual particle, will be updated with this present value. Secondly, we are going to work in the similar manner for the global level. All the particles are compared for their fitness values, and whenever we are getting best fit value, we are just going to update our fitness to G best level. The global best will be updated accordingly. For the next time, we are just updating our particle velocity. When we get the fitness best fit values, we update our parameters. For the particular search space, every time we have to update our parameter. We just analyze our iterations and then updations will be done for those particular parameters. First of all, we just update our velocity, and second time we are updating our position for those particular particles. The position, again, it is connected to our threshold value. It will be again compared with the threshold value because we have some we have to reach up to some optimized solution, and it will be defined by that threshold value. In case if we get particular solution after that RMSE comparison, again we can move to saving of that optimized results. We are just getting the optimized result and we can stop the algorithm. Now, what are the advantages of PSO? Why we are just going for PSO? Even there are some other techniques, for example, GA, BFO, and BAT algorithm. There are so many algorithms, and people are currently also searching some other optimization technique. But there are some advantage of using PSO. The first one, if we compare it with GA, in case of GA, we are just working for a single particle or 2 or 3 particles, and we are just analyzing their genetic behaviors. The parent are child and they are connected, and their particle moments will be updated. But in case, if we take our real life situations where we have to solve some certain critical problem, if one person is working for that problem, it will be optimized in more time. He will take obviously more time to optimize that solution. But if a team is working for that particular problem, they will be able to get solution in much less time. In the similar manner, if we compare GA with PSO, in case of PSO, we are having a group of particles, and those particles are working for a optimized solution. So it is much better to get the estimates, much better to get the optimized results, and iterations will be updated in much better manner. So it is insensitive to scaling of design variables, efficient global search algorithm, because we are just assigning a search space to all the particles, and every time they are going to update their position on the basis of p-best and g-best value. So it is working on global basis. Even we can consider a large application area, and we can assign more particles, because every time they are going to share their information. And we can even use some topologies also in case of PSO. Those topologies make our solution much finer, much better, because the topological manner, all the segments are connected to each other, and they can easily share their information on final basis, so that the comparison can be made much easier manner. We have very few algorithm parameters. For example, in our case, we are just taking the velocity and position. We are just working with 2 parameters, and they are updated every time. In case if we have only one particle, then we have to initialize more parameters for that, because we have to make more effort to get the optimized solution. It is derivative free. It is easily parallelized for concurrent processing. Now, more particles, a big group is working for certain optimization solution, so it is obviously much easier for them to get the optimized results. They are working in a group. Comparatively simple to implement. If we compare it with some other algorithms, some other optimization technique, these algorithms are comparatively much easier to understand as well as to implement. Now, PSO is currently working for so many applications, such as object tracking, path planning, as I have discussed the first topology in neighborhood case, signal processing. It is also using the optimization techniques, telecommunication application, and the last one is image processing. In our case, we are typically working on the image processing case. And now I'm just going to discuss the brief about the connection between PSO and digital image processing, on which we are just working. First of all, what is digital image processing actually? A field where some mathematical operators are implemented over captured images in order to process them to some desired results. We are just taking some images. They can be some blurred images, some noisy images, or some camera corrupted images. We have to get final results from those images. Sometimes you might have discussed that we just try to restore our old memories. We just take our old photographs from our childhood, and they are just a little faded. We try to restore them, and some photographers are very efficient to restore those images. Even they can develop colored images from our black and white images. In that case, they are using some optimization technologies, and the PSO can be implemented over those cases also, because we just have to restore those values, and we are assigning some particles to do that operation. Those particles will be working continuously to update their values, and some optimized solutions will be obtained from those images. Now, the purpose of image processing can be divided into following 5 groups: visualization, image sharpening and restoration, image retrieval, measurement of pattern, and image recognition. These are different applications in the field of digital image processing. It is further divided into certain applications, and PSO can be applied to any of these, and the results will lead towards an optimal solution. The optimization techniques are predefined. As I have told earlier, that we are just working to get the optimal solution. Our target is to get an optimal solution, so everything is working to get that solution only. Our all focus is determined to that one, and depending upon so many factors, every time we are assigning some values to those particles. In case of image restoration, as in case of digital image processing itself, we can work on image segmentation, image enhancement, and some other parameters also. In all of those, PSO can be implemented. But we are just presently working on image restoration. I'm just showing an image here that I was just telling in a previous slide, that we sometimes take our old photographs and we try to restore those old memories of our life. We have to get some better result for those images. So some photographers are much efficient to get this type of results. These results are actually implemented with the help of particle swim optimization, because we are just assigning some parameters to remove these values. Here you can see some noisy or blurred particles. We have to update their position to better intensity level so that a better image can be developed like this. So the complete image is just it is completely revolutionized, and we are getting much finer result with PSO implementation. The restoration attempt to reconstruct or recover an image that has been degraded by using a prior knowledge of the degradation phenomenon. Now what we are trying to do is, here we are having a degradation function that is denoted by H. Second one is restoration filter, and third is noise. We are just looking at these three blocks. In case of image restoration, we are having these three things. The restoration filter, it is implemented after the application of PSO or other optimization technique, whatever we are going to use. We can have median filter, spectral filter. There are so many filters already defined in DSP applications. The degradation function, this is our main focus. Whatever we have to do in PSO implementation, we are just going to recover this degradation function. By what value our image has been degraded? As shown by the previous slide, this image is degraded by certain values. We have to just get information about that degraded function, and that degraded value is required to be stored with the help of optimization technique. Although we are having here noise also, but this noise is much easier to remove with the help of some filters. For median filters, we can use spectral filter. There are some other noise models also that can be used to remove this noise basis. But in case if we are taking some blind images as well as some non-blind images, in that case we have to optimize our degradation function. Our major focus is for this. We are considering this fxy as our input and gxy as our optimized solution, whatever we are getting after implementation of PSO. There are some equations you may easily see in the Gonzalez, that is referred for digital image processing more frequently. If we are having certain input image fxy, as we are taking in this case, it can be a blind image as well as a non-blind image. What we have to do is, presently we are considering that this fxy image is degraded, blurred by some amount. For example, if we have captured an image on satellite, in some cases if it is getting some poor results and we have to restore those values, that will be called as a blind image, because we actually don't know what that image must tell us. That is a blind image for us, for the processor. We have to estimate some parameters for that particular image, and then this degradation function will be optimized for that particular image. What we are going to do is, we are going to make some analysis on this image and a function hxy that is defined as a degradation function, and we are going to optimize this every time with the help of PSO. Then we have to implement PSO for image processing. Our major focus will be degradation function, as I have told earlier. We are just trying to implement certain MATLAB codes. It is much better to implement our PSO with the help of MATLAB, because we are much familiar with MATLAB in case of our research type applications, and it is much easier to initialize our function in case of MATLAB. And we have to just optimize the degradation function to best values, best possible value that can provide us a optimized solution. For this, we just need to consider certain parameters, and those will definitely depend upon our application. Whether we are going to restore images, whether we are going to segmentation, work on segmentation procedures. And it is possible to implement PSO for blind as well as non-blind images, as I discussed earlier. And once we are able to determine precise value of that degradation function, we can restore that image, that particular image on which we are working, and all the efforts are just going to optimize this degradation function. Whatever we have to decide our algorithm, whatever pseudocode we are going to design, we just going to focus on this degradation function so that it can be optimized to much finer results. Whenever we are going to compare our degraded image and original image, we just compare those values to estimate some parameters for that degradation function so that it can be removed from the image on which we are just going to process. The example I am showing is satellite image processing, as I have discussed earlier. So this was the complete overview about the PSO and how we can implement it in our application. So many researchers might be working for this, and even so many results can be easily found on internet also. Even I am just showing some references on which those papers I have worked, and I have studied some parts from these analysis. Everyone have initialized their own parameters on the basis of their application requirement, and they were just working as like for here we have support vector regression. It is some different technique in PSO itself. Some different parameters are initialized with the help of this support vector regression, and people used to work on search efficiency function also. Some are working on just getting the enhancement in images. So I have just referred few papers to get the analysis about the PSO, and the restoration part is going on. We are just implementing the MATLAB codes, and soon I hope we will be implementing our results, and hope they will be getting to much finer details. So that was all from my side. Thank you very much. And now we are going to stop our session just for a lunch break, and we are going to meet after. Okay, we are just going to have a query session. If you are having any kind of queries.
Yes, at Maharaja Surajmal Institute, we have any questions?
Hello.
Yes,
Hello.
sir.
Ma'am, am I audible?
Yes, sir.
Just want to know what is this local best? Why we have to find this local best?
Okay, sir, actually, you need not to define this local best value every time. If you are going to optimize your solution, if in case you are working on topological basis, if you have decided some neighborhood for your optimization, in that case you will be working on local best values, because in that case you are working on some search spaces, and that search space will be divided into some local best values, and those local best values will be defined for that particular area also.
Then in that case, we also have to find p best or not?
Yes, sir. P best and G best will be always used, and local best is used only in case of topological behavior of PSO. G best and P best will be always utilized.
Okay, okay. And
Yeah.
topological behavior, there are 5 types of topological behavior. How we will identify which one we should use?
Sir, actually it is completely application dependent. You can just check out some reference papers on internet. There are so many sources, and they are just going to tell you about advantages of using some certain particular topology. If you are using ring topology, there are only 2 particles that are going to share information. In case of fully connected mesh type technology, all the particles are going to initialize their parameter estimations, and it completely depends upon your application. Because if you want to get results in much less time, you need to define parameters accordingly. It will depend how much time you are assigning to particles to get the optimized results. On that basis, you are going to define your topologies also.
Okay, ma'am. Thank you very much,
Okay.
ma'am.
It's okay. Anyone else?
Okay, at JSS Academy, we have any questions?
Hello, yes, sir.
Yes, sir.
Ma'am, you are audible.
Yes,
No,
ma'am.
ma'am, it was very interesting session.
Thank you, ma'am.
We don't have any questions. Thank you so much.
Thank you, ma'am.
Okay, at last. Why? Yes, at YMCA.
So I think all the queries are done. if you still feel some queries, you can just update on our websites also. There are some sessions on NITTTR websites also. You can check those also.
Okay. Thank you.
Thank you very much.
Thank you. सेंटर से आए नहीं मेरे ख्याल से। खाली लग रहा है। अच्छा है। Okay. So, okay, good afternoon, everyone. So, in the last 1 hour, you must have heard about the optimization algorithm, that is PSO algorithm, particle swarm optimization, delivered by Ms. Jagriti. And now Ms. Ayushi will be giving the lecture on BAT algorithm, BAT algorithm. So I'm sure that you must be beneficial from this lecture, and I hope that in the previous lecture also you must have gained some knowledge about the optimization or the PSO optimization technique. Now it is your own wish that in which field you have to use. You can use in image, or you can use in cloud computing, or you can use in some other field. The optimization can be used in any field. Now in which application you want to use, that is your own wish. Now we are giving the lecture on BAT algorithm. So Ayushi, you just come and give the lecture.
A very good afternoon to one and all. I'm Ayushi and I'm going to present this seminar on BAT algorithm. The topics that will be covered are the introduction, that is, what is BAT algorithm all about, why are we using it, and the rules to follow this algorithm, the processes involved. Flow chart that will give you the step-by-step introduction, everything, every parameter, including how the matching is done, the comparison is made, and how we get the optimized solution. Then applying it on the digital image part by using an example of segmentation, which involves multi-level thresholding. Advancements. As BAT is a very new algorithm, it was launched in 2010, but theoretically many more advancements are also available for this. That will be discussed soon. Application, in which areas it can be implemented, comparative analysis, and any of the algorithms are available for different applications, and why is BAT much more preferred nowadays. Advantages and the improvements required for this algorithm. Then definitely the references involved. What we all know what is a BAT, and how does it, the very fact known about it is that it can't see at night. But the reality is the other side of the coin. That is, the bats have much more sharp senses as compared to any other living beings in Earth, even including human beings. And that sensing is based on echolocation. Echolocation itself comprises of two words, echo and location. Echo is the pulses involved which the bat sends to its prey. Echoes can be in the form of frequencies or the wavelengths. Here we'll be considering on frequencies, we can take it either way. And the location. By sending these pulses, the bat recognizes where its target or the prey is. And this echoes will help him find the location of them, and it will be directed towards that direction. So it uses the sonar echoes. Sonar stands for sound navigation and ranging. It is the same thing which is being used in submarines or underwater satellites, and there's the same concept which bats also uses to detect and avoid obstacles. Detection is for its prey, the target it wants to have as its food, or the obstacles, maybe the larger animals from which it wants to save itself. So these pulses are sent in the form of frequencies, which is reflected from the obstacles. Here you can see this is an obstacle involved, a butterfly or any other fly which is taken to be its prey, the target bat wants to attack. It sends its waves, the reflections, in the form of frequencies. Whenever the frequencies hits its target, it gets reflected back. And this reflection will tell bat about its location, the ideal location, and how to proceed for it in the same direction. The sending and reception of the sound waves in the form of frequency will give us a time delay. And this time delay will help us to find the distance of the bat from its prey. So these reflections may or may not be exactly what it wants. It may not be a target, but instead it can be a group of another bats which are looking for the prey. So it matters. This time delay will give us that is it a target, a prey, or the other group of bats that is looking for the prey. Now coming back to the technique, the algorithm we are trying to apply is the pulse rate. We are considering two main features, that is the pulse rate emission and the loudness parameter. Whenever bat emits frequencies, two parameters will keep on changing. When it is at the farthest distance from its target, it will have maximum loudness. And as it approaches the target, the loudness keeps on decreasing. And while the pulse rate emission increases, as it will reach its target, it will come close, it will be somewhere here, proceeding towards the target. So the rate of pulse emission will keep on increasing to very high value. And when it is, we can't say it's infinity, but a very large value, we will know that it has reached its target, the prey has been taken, and it's a complete successful algorithm. As already discussed, it is a probability-based optimization techniques. So the probability lies between 0 and 1, and that is the reason we take the pulse rate emission from 0 and 1. So here are we have a bat. I'll just change the color for this. Okay, we have a bat which is trying to find its prey. It sends different frequencies all around. It can be omnidirectional or in a specific directed way, maybe at a 90-degree angle, or it can define the way it wants to send the signal. And there are many hindrances on the way. Here it is taken C1, C2, and C3. That are three distances, three distant objects. So from here, the reflected waves come, and we know which is the which has the smallest distance, and in the very same direction the bat will continue to move forward. So now we know that the bat knows where its prey is. It gets the location of the prey. It knows the distance between them by calculating the time delay. And now the functions that are being updated, the main thing that makes bat algorithm very useful and efficient is the parameters it involves. In PSO, we saw the two parameters involved were position and velocity. Here, three more parameters come into picture. That is, the position is still there, velocity is also there in the same way that is being used in the PSO. And now we have the loudness parameter and the pulse rate emission. Being it a probability function, we define it both the functions in the range 0 to 1. And the frequency, because frequency will tell us the distance of the prey. Now, as it being the probability, we know the changes will be taken care of. If we have one bat here, and the other group lies here. We have many groups for the bats. Let's take three directions. That are the dimensions K and the directions. We have three different groups of bats which communicate with each other. This is the main initial starting position. Now we have a distance here. Three distances involved. So the bat will know what are the actual distances, where it needs to proceed, and for this we need to know the idealized rules involved. Initially, we've already talked about the rate pulse emission lying between 0 and 1. That will be considered to know the proximity, the distance of the target. Then the echoes used to detect the exact location of the prey. These will be transformed into frequencies, the pulses, and then that will be used to navigate the distance. Time delay parameter tells us the distance, and that will be proceeded further. The loudness can vary from 0 and 1. We'll be initializing some values, A minimum and A maximum. A represent the loudness here. So it should have a large value and then proceed to the lower ones. It should acquire a minimum value, A minimum. The equations involved have 5, as the parameters are also 5. These are the frequency, velocity, and position variables, which will be updated for every iteration, every position change of the bat. Frequency also has a finite value, so it should have a maximum and minimum as well. So it is given by the current frequency position is given by the minimum value, then adding the difference of the both minimum and maximum, that is the range we want to define, with a constant random vector in which direction it should perform. Being it a probability, we are considering it to 0 and 1 for the uniform distribution. Then the velocity updation, if we assume that it is at 0, 0 position, it is just at the beginning, then the initial and the previous position will remain the same. Otherwise, it will take the previous position, the previous iteration position of velocity. Plus, there's a change here as compared to the other equations being performed in other algorithms. XIT is the position of the present pixel minus the best current location. That is the global best which was available all throughout the pixels, all throughout the image. And we multiply it with the frequency vector to give it as a velocity direction. The position updation is the same as was done in other algorithms, that is taking care of the previous location and the velocity factor. We just talked about the current best location, but we need to know how it is found out, how is it calculated. So we consider the x new, that is the present we want to calculate. While considering the older one version, we take the older previous one, and some variation has to be made so as to optimize it. We take the probability, that is del, and a raised to power t. Del is a random number. We take it not from 0 to 1 but minus 1 to 1, as the intensity at the pixel can be increased or decreased. Maybe the available frequency or the available intensity is not good enough. It's too high for the location. We need to decrement it. So it ranges from minus 1 to 1. And 80, the loudness factor, we have already discussed before. So we know as the bat approaches its prey, it will the loudness factor continuously decreases. It cannot be 0, but the experimental value shows us that it goes around to 0.1 value. It can ever be 0 because the perfect optimization is just an ideal concept. And the rate of pulse emission increases. It will be very close to the value of 1, but around 0.95 is the estimated value experimentally found. Then the variation. We know that bat is not going in a perfect straight line. It is not a linear distance. So there's an exponential decay for the rate of pulse emission. Considering the rate of pulse emission, it is exponentially decrementing. Gamma is just a constant which can be defined by the user as per your application. T is the number of iterations which we want to continue, and Ri naught is the initial rate of pulse emission which we took. It is not the previous one but the initial one which we wanted. And the loudness, that varies exponentially, it decays exponentially, and alpha is approximately equal to the exponential E value, but not exactly. So we are using alpha, not E. And it obviously varies with the previous one. Talking about the bats, we have to vary to, we want to know that what are the actual frequencies and wavelengths on which this algorithm works. The frequencies are 20 kilohertz to 500 kilohertz, which will be optimized while using it in the MATLAB coding. And the wavelength is from 0.7 to 17 mm. Now, the step-by-step procedure, how to perform this algorithm. We need to know everything about it, starting from, we are taking an initialization position, consider an image, and we are at this position, the 0, 0 pixel. And we want to move to the highest position available, that is the other end of the image. So we need to set some targets, some constraints to perform this algorithm. Initially, we'll take an objective function or the fitness function already talked about. This will vary according to the application. For segmentation, it will be something else, and for restoration, we need to change the fitness function. It is application specific. So position and velocity along with the x-best solution, we have to initialize all of these. They are not zero, but we'll be giving it some finite values. Assume it to be 0.5. Let position be 0, 0. Velocity be something between 0 and 1. And the x-best solution can take any value depending on the application. Then the pulse rate, emission, and loudness. 0 to 1 we have to define. We can't take 0 values for either. We'll take the mid values. Assuming that we want to increase one and decrement one, so we'll be taking the mean of it. Then the number of iterations required. This directly depends on the time consumed for performing any algorithm. For the successful completion of an algorithm, we need to know how many iterations did it take to completely optimize the image. And the number of solutions. And that is the library we have to store the images. And that is the number of options we know for every pixel. We generate a new solution for every pixel. Like we are in this region, we are at 0, 0. We need to generate a new solution every time for every pixel we move on. We generate a new solution and we check it that the existing solution on that pixel, is it already better than the existing one, or the newly generated is better. If the new generated solution is better, we'll accept that solution and move downwards. That is, increment the number of solutions and the iteration number by 1 and save in our library. But if the existing solution is not good enough, we have to generate a new solution. We have to proceed with that. So for this, we are following probability. We take another random number that belongs to 0 and 1 that will be randomly generated via code. We compare it with the two variables or the constraints we have already talked about, that is loudness and pulse rate emission. Initially, we'll be taking the pulse rate emission. If the random variable generated is greater than PE, that is a pulse rate emission, because we want that pulse rate emission should increase, so just the random variable generated should be more than the pulse rate emission. If yes, then we'll proceed further. But if it is not, we know our solution is not optimum, it is not optimized, we need a much better solution than this, we'll go back by generating a new solution. Just in case if this is a good one, we'll check for the other parameters. That is, we'll generate a local based solution and a global based solution. Local based solution is a solution like we are here in this area, we have a mask that is to be followed. We check in this area, the neighboring cells of this area, that what is the best solution available. That will give us the local best solution. And the global best solution is the solution of the total entire image, of the total entire neighborhood. So these two solutions are generated. We have got the local best solution and the global best solution. Now we check the next parameter, that is the random variable for the loudness parameter. So now we know that loudness should decrease. If we are getting an optimized solution, the loudness should decrease. If that is satisfied, the last point to check is the fitness function we have already talked about, which is considered different for every application. The fitness function should also decrease for the present value. What was already existing, it should be less than the existing one, the new. We accept this solution as the x-best solution. We increment the number of solution, increment the number of iterations by 1, and then we check, is the solution is the number of iterations equal to the maximum number of iterations. That is, the maximum number of iterations depict the total width and height by width ratio, m by n. That is the total maximum number of iterations. We need to optimize the whole image, so we consider the maximum number of iterations. If the whole image has been optimized, the algorithm has been performed on every pixel of the image, then we stop the algorithm, else we'll continue for the next image, next pixel in the image. While incrementing the iteration, our position and velocity as well as the frequency also gets incremented. They get updated every time when these are incremented as per the equations. So what we are trying to implement for our thesis work is that we are taking an example of segmentation that is a part of the digital image processing. We are trying to do the multi-level thresholding. In this, we are taking different levels for the thresholding. We can define many levels, let it be K levels of optimization. For the beginners, we can just say that these are the different thresholds we have defined. Maybe a grayscale image, we want to change the pixels lying between C2 and C1. The pixels lying between C1 and C2 will be given a definite signal and definite intensity, that is thresholding. How many number of pixels is being used for in between this level? So we take the theory of histograms. The number of histogram is given by the number of pixels having this level Hi, and I are the number of pixels that have this intensity value. They are L gray levels. C0, C1, C2 till L, it can go up to L. So L are the number of gray levels involved, and the range is defined from 0 to L minus 1. It is a probability function, so normalized probability is taken, that is given by Pi, and it is equal to Hi, that is a histogram, divided by the M, that is the total number of pixels available in any image. The fitness function for segmentation is given by this formula, H0 plus H1 up to Hk. For every level, this H function will be calculated. And the general formula for this is given here, Hk, which depicts the negative of the summation of Pi by Wk. Pi is the same histogram divided by the total number of images, pixels in an image, M. Wk is a total cumulative probability function. We divide the initial one from the total probability function, we take the log of it for the same values Pi by Wk, and we get the value of Hk. It is negative because we can say we want the loudness to decrement, and this will definitely vary for every application. Hk will change for segmentation, for restoration, for enhancement, or everything, for every different application. So how to proceed in a MATLAB code? We have already discussed the general part of the BAT algorithm. Now we have also taken an example of segmentation, which is regarding the digital image processing. But how to use it in a MATLAB code? We begin to write a code in MATLAB. We start with some parameters, considering all the 5 constraints, variables, frequency, position, velocity, loudness, and pulse rate emission. Then we are using a known image. We already have an image. We are trying to implement that on the BAT algorithm. We try to deblur it using any type of noise. It may be impulse, salt and pepper noise, or Rayleigh noise, or gamma noise. We can take any of it. Now we try to call the function, which has already been discussed, like the example of segmentation. We make the algorithm for this. We make a MATLAB code for the segmentation. Now we call it in the MATLAB. As the BAT algorithm is called, we compute different values of fitness function. H0 till Hk were discussed. We calculate these values here in the fitness function as a fitness function. We save them in the library, and then it goes back to the main functions. Every function which we have got is deconvolved. That is, the errors or the noise is being avoided, is cleared using it. We save the solution and we compute the next best solution from them. If it was k dimensional, we will get k best solutions for every image. So we'll get a vector of it. Now we'll compare both the solutions. One from what we have got in the MATLAB algorithm, and the one we have reached by deconvolving that function. If these match, these should match if we are applying it successfully. If they don't, that means that the function that is called did not act properly, had some flaws, so we need to go back to the function again. If these match, we know that we have successfully optimized our image. So BAT has been done, though it was done by Xinshe Yang in 2010. It's a comparatively very new method for optimization techniques. But many more theoretically advancements are being talked about in research papers as well. Some of them are listed here. First being the multi-objective BAT algorithm, MOBA. We know that we were optimizing just one image in we just had one image and we were trying to optimize that. But certainly in real-time applications, we want much more optimized ways. A satellite is observing the traffic parameters. It is clicking the pictures of traffic in a very crowded area. It is also taking care of the matches being played in the grounds. So many more things are being done at the very same time, and we need a great optimization for the same, all the same at a very fast and efficient way. So this is being MOBA is being used for the same in engineering tasks. It is being implemented, and to notify that everything in considering a building, we need to take care of the corridors, the classrooms, everything. So that is being optimized with the help of MOBA. Fuzzy logic BAT algorithm. As we were just talking about the 0 and 1 ratio, the probability lying between 0 and 1, fuzzy logic is one of the techniques which can also be implemented with the BAT algorithm, as it does not just belong to the binary. It's not just 0 and 1, but a many valued function which varies between 0 and 1. So if they both are combined, they can actively be used for the optimization. Binary BAT algorithm. These are specific application specific algorithms which can be used where we just know that we'll get either a 0 or a 1. There will not be any intermediate intensities available. So to reduce the complexities, we use binary BAT algorithms in these cases. Improved BAT algorithms. These use the loudness and pulse rate emissions parameters along with the Levy flights. This is also a function which is based on the probability of Cauchy probability function and normal probability function. So by combining all the three, we have got very good results, and by using different functions, like experimentally 70 different functions have been tested, and it is found to be very efficient. And one of them is also the differential operator and Levy flights. Already discussed about the Levy flights and the differential operator. That is a very good mathematical tool to calculate any of the errors or the noise present in any image or any other application. So combining these, we try to optimize our solutions and get the efficient solution of any problem. The applications, though, are not limited, but the most specific use are being done in the image processing. We have already discussed an example regarding that. Continuous optimization that can easily be done with the help of MOBA, multi-objective BAT algorithm. Combinatorial optimization and scheduling for checking the multiple tasks being performed at the same time. Inverse problems, that is and parameter estimation. We need to calculate some MSEs and RMSE or MMSE and get back to the restored image. It is not possible that a non-blind image is always available. We sometimes need to optimize an images from the satellites as well. So inverse problems may be involved to get back to the much more clear images that we have acquired from the sensors or the cameras. Fuzzy logic BAT algorithm, definitely it can be used to increase the optimization. Comparative analysis. Now we have already discussed about the PSO. Now this BAT will be compared with some of the other algorithm techniques based on some of the features, and why is this better. First, considering the BAT algorithm, already talked about the echolocation behavior of the bats, while the firefly algorithm is based on the arching behavior of firefly, also called the jugnu's, and the cuckoo search, that is based on the bird's brooding. Cuckoo is a type of bird which broods. The brooding of birds, how does it lays its eggs, and how does it utilizes the nature. Then it is defined, BAT we know it is defined by the pulse rate emission and the loudness, while the firefly is used by the brightness and the attractiveness of the fireflies. Cuckoo search, whenever a cuckoo lays its eggs in the nest of other birds, it distinguishes its own eggs using the color. So that is the fitness function will be defined by the color of the eggs in this case. The features involved for the bat is that it is very accurate. It is very time saving, because if we know that we haven't met any of the one of the parameter, maybe loudness or the pulse rate emission, it will go back to generate the new solution. So it is very time saving and accurate as it considers many parameters involved. 3 of the functions are definitely compared, and the rest 3 are taken care of and updated every time. It is very efficient in this manner. Why the firefly will give us a good result in a very less number of iterations. So it is very fast, but yet we can experimentally it is found that bat is faster than firefly as well. Cuckoo search, it's easy to implement, but it is not much efficient. Bat has been applicable in almost every field we are talking about, even the digital image processing involved or the nanotechnology. It is being researched even in these ways. So BAT is definitely better as compared to the others because they are application specific areas algorithm. Some more advantages, why it is better, why we are using it, and why the research is being made only in this direction is that automatic zooming. Nowadays, cameras are a very important part of our life, and we know the pixel quality depends on how well you can zoom it and the image does not deblur. So the BAT algorithm provides us a very good zooming power. Even if you try to zoom it to quite a level, it won't give you a blurred image. It will be very noise free, and this is the reason why BAT is better than much of the algorithms. Parameter control, yes, we are considering loudness and pulse rate emission. It automatically finds. Initially, we'll explore one area, that is, if we have an image, we take a sub image of it. We won't apply it on the whole image altogether. We take a sub image part of it. We'll explore this image and then make the changes to it. Then exploiting it, we move further to the whole of the image. That is, sub image is applied, the same application is applied to all the complete image. Then the frequency tuning. Though we know that echolocation is not directly being used in this algorithm, this optimization algorithm, but yes, the frequency is still being used and it is being updated at every point, at every pixel. Advantages. The codes, MATLAB codes involved, or the easy understanding of this algorithm has made its use in the easy implementation. We have wide ranges of problem, and now we know the distance is not linear for any prey or bat. It is non-linear, it can be wavy, it can vary in any form, so it can be easily applied to non-linear applications. It gives us very optimal solutions, and it works with complicated problems as already seen. Segmentation in multi-level thresholding can be very hectic, but BAT algorithm has given it a very new definition. It converges very quickly. That is, the convergence rate for this BAT algorithm is very small. It means we get the results in a very less time. So that makes it really useful. Auto zooming already discussed about, depending on the parameters, loudness and pulse rate emission. As we were discussing in the flow chart, we were saving it the number of solutions in the foundry. We just came across that for a specific pixel we have more number of options available, that is, more number of solutions available. This makes the pixel or the image very precise and very clear, so the noise can be easily removed. You have much more number of solutions available for that. Everything has its pros and cons. So these are not exactly the cons, but the improvement that need to be done for the BAT algorithm is when we are taking a small picture or a small size of a picture, the BAT algorithm is very precise, very efficient. But while talking about huge pixels, like a very big image, then the convergence rates slow down. That means it will take a little more time as compared to a small image. It is not directly proportional. If a small image is taking T1, then a double size image will take time 2T1. It's not like that. It literally slows down. That is the area it has to work upon. And for various applications, we need different kinds of fitness functions. So we need to have a complete knowledge about every field we are talking about. And as it is just a new algorithm which is being implemented and researched upon, it is not very clear that what will be the best values or the best pixel quality we have for an image. That's all for the BAT algorithm. Thank you. Any queries? Sorry. Any query from Maharaja Surajmal Institute?
Yes,
Any
hello, madam.
queries?
Hello.
Yes.
Good
Yes,
afternoon,
please.
madam.
Good afternoon.
How we can decide the frequency of
Ma'am,
echo?
ma'am, experimentally, we have to evaluate some parameters and we are defining it in the range of 0 and 2, the minimum and maximum values. For
Yeah.
every application, it will vary, but we are defining it from 0 and 2. It will keep on changing, but maybe for segmentation or restoration, it will lie in this range only. That is given
So,
by the Xinshe Yang, which actually proposed this algorithm.
so it is equivalent to limit. 0 to 2 is the search area.
Yes,
0 to
ma'am,
2.
actually. Because this will help us in defining other parameters. If we try to restrict, these are the parameters which we have already restricted, like the position, the velocity. We need it to optimize the solution, and we will be changing frequencies, getting updated by every step. We need to change loudness and the pulse rate emission, which is dependent on the frequency. So we need to define it in a range.
Okay.
Ma'am, what is this Levy flight?
Sir,
Levy
Levy
flight.
flight is an algorithm which is based upon the Cauchy principle, Cauchy probability function, and the normal probability function. It is defined by the probabilities of two different functions combined together. And now we are using it with our BAT algorithm, considering the parameters loudness and the pulse rate emission.
Okay. Thank
Any other questions? Any other queries? Any queries from YMCA? JCS Noida, any queries?
No, no, ma'am. No, ma'am.
Thank you. Okay, so now as BAT algorithm is already complete, my colleague Neha Sharma will be discussing the next optimization technique, that is BFO, bacterial foraging optimization. Thank you.
Madam.
क्लिक भी नहीं हो रहा. Good afternoon, everyone. My topic for today's session is bacterial foraging optimization. Here are my contents: introduction, basics of BFO, then optimization steps that are followed in this optimization technique. BFO has many applications as in comparison to all other optimization techniques, but mainly I'll talk about BFO as a denoising filter and will work on this area. Then the flow chart of this optimization algorithm, its advantages and applications. Starting with all these techniques which we are talking about here today, optimization techniques, BAT algorithm, PSO, BFO, and fuzzy logics, they all come under the concept of soft computing. Why do we need soft computing? For the systems with imprecision and approximations that cannot be modeled and examined with the already available mathematical tools, we go in for soft computing. Now, soft computing, what it do? The techniques in the recent past, they have been developed for denoising filtering, denoising the image and denoising filters. I'll basically take the example of human body, and for denoising filters, there we require in the for managing the for getting treatments of the various in the medical domain for treating various diseases. For that we need denoising the image, and for denoising of image we need a denoising filter. Adaptive algorithms along with denoising, they perform well when we use optimization techniques. Now talking about introduction, BFO is a nature inspired technique to find the optimum solution of the problem. In 2002, Professor K.M. Passino, they introduced the optimization technique known as BFO, which is based on the social foraging behavior of E. coli bacteria that is present in human intestine. Now, social foraging behavior, it refers to the foraging technique, that is the search of food. Bacteria, they'll move into the direction of the increasing nutrients. Here in case, when we related with the image processing, the cost function will define as the minimum error. Mean square error, that is the cost function, it has to be minimized. The more it is minimized, the more fitness function we get there. Now, bacterial search for nutrients in a manner to maximize energy obtained per unit time. The total energy it is gaining from the nutrients per the time it has utilized the time for searching that nutrition direction, that is the optimization parameter. Maximization of such a function provides nutrient sources to survive an additional time for the activities that are required to be done by the bacteria. This formulates the foraging problem as an optimization problem. Now, relating it with the image processing systems, we need the image pixels and to move it in a direction where we get less noise and more of the fitness values. Individual bacteria, they communicate with others by sending the signals. During foraging realization, the real bacteria, the two basic operations are being performed, swim and tumble. This will be covered in the first step of the foraging optimization. Now the basics. The bacterial foraging is an evolutionary algorithm which estimates the cost function. The cost function in this example for denoising the image which I have taken is our mean square error minimization. We have to work upon that. After each iterative step, as the program proceeds, it leads to the progressive better fitness. Better fitness means less cost function. And the parameters to be optimized, they represent the coordinates of the bacteria. We can talk about bacteria in case of human intestines or the optimization technique BFO, but when we relate it with the image processing, we'll actually take the coordinate system. The search space area where we need to minimize the error function and optimize our cost function. The parameters are the coordinates of the bacteria, that is the position at which a pixel will be placed. The parameters, they are discretized into the desirable range, and each set the values they represent in the space coordinate systems. The one bacteria is positioned. Now, the complete search space area which will have at each position will have one bacteria, and after each progressive step, the bacteria it moves to a new position, that is new coordinate system, depending upon the when in comparison to the previous pixel value, if the cost function is less, it will tumble, it will change its direction. But if the fitness value is not that less, cost function is same or either more, then it will not make a movement to that direction. And at each position, cost function is calculated. With this calculate value, further movement of bacteria is decided. Means the cycle goes by, first we initialize certain parameters, then we check the cost function, and after every checking of the cost function, a movement will be made by the bacteria. And after that step movement, again the cost function will be evaluated till the complete search space in the coordinate system is being completed in that manner. This finally leads to bacteria to a position with highest fitness. Now, comparative to all the pixels in an image, it will make comparison or movement in the complete search space coordinate system. and it will reach to a position which is the highest fitness value. There are 4 steps. First is chemiotaxis step. Second is swarming, reproduction, and elimination. Now coming on to chemiotaxis step, this is achieved by swimming and tumbling. Now there are 2 processes in chemiotaxis, means movement what the bacteria will make. Either it will swim or it will tumble. What is swim? A unit length in the same direction, it refers to swim. If a unit walk in the different direction or as in comparison to previous direction, that is called tumble. Now, when the bacteria it meets a favorable environment. In case of bacteria, the favorable environment is the direction that is increase in the nutrients and noxious free. And in case of pixels or images, it is the pixel value that has less of error value as in comparison to the previous pixel values. It will continue swimming in the same direction if the nutrients increase in the direction of swim. It will swim in the same direction. Otherwise, if the nutrients are not increasing, it will tumble. These are the 2 steps, and the bacteria, it keeps on operating between these 2 positions in its entire lifetime. This is the chemiotaxis step. Swarming. E. coli bacteria, it has specific sensing, actuation, and decision-making mechanism. In each space, in each coordinate system, each bacteria, it coordinates with other and decides for the local and the global based fitness functions. As each bacteria moves, it releases an attractant to signal the other bacteria and to swarm towards. Swarm is like grouping. It will signal to another bacteria and they will group together and move to the next better position. Reproduction. After calculating the fitness value for each bacteria, reproduction allows the half-healthy bacteria to survive and reproduce. This is the main important point which leads to many applications and advantages of this very optimization technique, since it reproduces and it cuts short the very half unhealthy bacteria whose fitness value is less. And now we have to deal with only the left half of the bacteria, and those half bacteria, they are already having more of the fitness value. Hence, this leads to the advantage of fast convergence. This helps in generation of values of variables which are close to the actual values. Now, once we have deleted the unhealthy bacteria and working with the left of the healthy bacteria and their reproduction and elimination, this will lead to the results that are closer to the actual values. 4th step in this optimization technique is elimination and dispersal. Now, elimination, the chemiotaxis provides basis for local search, and reproduction, it speeds the convergence. The first 2 steps that we have talked about, the first step, it provides the local search, and the reproduction, it speeds up the convergence, as I have told. Now, why is elimination and dispersion required? To avoid the trap of bacteria in the local minima, elimination dispersion is done. If a bacteria will compare into a certain limited area, it might get trapped into a local minima. But we have to eliminate it and disperse it. In dispersal, what happens? A single bacteria, it gets divided up into 2 similar bacteria. Hence, the overall coordinate systems, it is equated with the same number of bacteria, but with the healthy one. Now, using BFO as a denoising filters, why do we need denoising? I'm taking here the case of, like in example, medical images. We require more optimized results, less of noise, so that the treatment can be done. We use denoising filters, and to denoise it, we need algorithms. BFO is one of the best that is applied in that case. It presents a soft computing approach to denoise the medical images. This is a bio-inspired algorithm that is used as a filter. Hence, we are talking of BFO being used as a filter for denoising. Requirements in the medical images. Like in medical images, the noise inserted are very miniature noises. Even the noise from a signaling to the bones, signals to the brains, and the body movements, they can also cause noise and interrupt with the actual or the targeted value of the image that we require to diagnose in that case. And we need to be eliminated for the better diagnosis. Now, for soft computing techniques, as I've told, they can either work in isolation or in conjunction with filters. Those filters can be either adaptive, median, or adaptive median filters or average filters. Basically, they have told here that with gradual Gaussian noises, BFO is used in conjunction with mean filters, and other type of noises like salt and paper noise, BFO is used in conjunction with adaptive median filter. It gives the capability to search the pixel without jumping or skipping. Now, one more advantage of BFO which we'll talk about is its accuracy. Now, how this accuracy comes, since the just like in case of the bacteria, it moves and does not jump, but it covers all the pixels one by one, thus it improves the quality of the image that we require. BFO is a soft filter for taking the diagram. This is adaptive median filter. We take a noisy input, pass it through the adaptive median filter, we get the output. This output to the median filter, it has reduced some noise, but not to that extent that we require. Hence, we subtract it from the original image and get the error signal. This error signal is used as the basis for bacterial foraging optimization, which will make updates for the weights, or either it can make it adaptive in the manner that it can increase the area of the swim. This will take up in the advantages. Now this error signal has reached up to, it has gone to, now first was our input noise that has gone to the adaptive median filter. This noise is subtracted from our original signal. Now this error signal, this is the signal that was not being removed by the adaptive median filter. Adaptive median filter was not able to remove this error. This has gone to the bacterial foraging optimization technique that will optimize its weight functions or its coefficient in the parameters, and then again it will move on to the median filter, which will again denoise the image and give the output to the original signal. In each time the bacterial foraging optimization is applied, in each iterative step, more number of clarity, more number of noise reduction, more amount of fitness function will be achieved each time. This was the case. Now ideal images, they are corrupted with noise. Noisy images pass through adaptive median filter. Difference in terms of mean square errors. This difference we do not take just simple difference, as earlier also in PSO we have studied. We take the mean square error between the filtered image and the original image. This is our cost function, and less amount of this cost function, more is the fitness value. Now to further go to the BFO algorithm, we have to initialize certain parameters. This algorithm, how much hectic it might seem to be when it comes to presentation, but there are basically 4 to 5 steps. First is initialization of parameters, then is evaluation of the fitness functions. Once we have evaluated the fitness function, we'll make a movement. That movement will either be a swim or a tumble, depending upon either the cost function is less or the cost function is more. After that, what we'll do, we'll check the swimming steps. We'll set a counter initially, because initially the bacteria has made no movement. Now if this is our search space, initial bacteria, this is ith bacteria, it is starting from here, this is set to 1. I equals to 1 will initialize this parameter. For each bacteria, for I equals to 1, we will keep on increasing the J parameter. J parameter will take as the chemotactic steps. For each step, here is the chemotactic step NC. NC. For each increment of I, again G is all the chemotactic steps will run, and till the time it is less than NC. This loop will run till the time J is not equal to NC but less than NC. Will again compute for all the next position, that is I will be incremented by 1 now. And then similarly chemotactic steps, now this number of swimming steps will initialize. Number of reproductive steps will check how much bacteria we have got for the fitness values, eliminating that and reproducing the healthy bacteria. Number of elimination and dispersal steps, that is NED, and the probability of elimination and dispersal. This is the variable, the number of bacteria that will die in this range, they will be eliminated and the equal will be dispersed in the coordinate space system. Now the cost function which we are dealing with, which we have to minimize in this optimization technique, is MSE, that is mean square error. This is this cost function. 1 upon Mn summation of this F dash, this is the filtered output. The output at the adaptive median filter that we have received, subtracting the target image and squaring it. This is the mean square error that we need to minimize. Now we have taken the filtered output as f dash xy and f a function of xy. But for the case of the pixels, now pixel to pixel operation is to be performed. Now we have to change these parameters. We'll take it in with respect to P of I, J, K, L. 4 parameters will be included now. It will depend upon 4 values. Similarly, this was for f dash xy. For f of xy, this will be R, X, J, K, and L. But now what is PIJKL? This refers to location of ith pixel, J is the jth chemotactic step, K is the reproduction step, and L is the elimination step. Similar way, in our algorithm will go by these 3 loops. One will be reproduction loop, other will be elimination loop, and first will be chemotactic steps. Once we understand all these parameters, their initialization, then algo becomes very easy to understand and implement. For the function fxy, we have taken it R. This is x is the target pixel. Now I was our simple location of the pixel that will take at the starting of our coordinate search space system. X is the target pixel which we need to make it equal to. Z is again same chemotactic step. K is the kth reproduction step, and L is the elimination step. Now instead of using this MSC value which we have used here, this MSC value will update this with the pixel values. This one, this function will use now. Now this is J will represent the cost functions, P of I will represent the adaptive filter outputs, and this R will represent the original values, and mean square is the whole square value. And J will represent the cost which we have to minimize it. This is J value, this is the cost function, cost of the pixel, and Ci, one more parameter that is initialized is C of I, that is step size in the random direction. This is the algorithm. Step 1, we'll start the algorithm, we'll initialize the parameters P, S, NC, NR, ND. What is P? Is the search space, this is taken to be 1. S is equals to M into N, that is total pixels in our image. NC is number of chemotactic steps, NRE is number of reproduction steps, and NED is elimination and dispersion steps. Now initialize I equals to 1. What we have to do after initialize, we have to compute the cost of the bacteria. J we took it as the cost. Now we'll make the difference between the output and the target image value. Clear? Now the J last will be updated by this difference value which we have calculated. We'll update this value into J last, a variable. Now tumbling means we have taken up the next chemotactic step if it tumbles. This is also the difference and mean square value. Now, after making a tumble or swim, we have to initialize a counter that will take care of how many tumbles or swims it has made, setting m equals to 0. Now, if we'll compute, if the ji of 1 which we have find out, if it is less than the last calculated value, the bacteria makes one more step in the direction of tumble. Clear? It will make a change if the value cost function, J is the cost function. If this cost function is less, it will make a move in the direction of tumble. Now one direction has been made, we'll increment this with 1. Earlier this was 0. Now if we'll calculate if m is less than n is. Now this counter, if we'll check it for number of the swimming steps, ns is the number of swim steps. If this becomes less, then we'll again compute for the cost function value. Otherwise, we'll check for the I. I refers if all the pixels, all the bacteria have been checked in this space. If I has completed all this value, if I has reached the search space is ended, we'll end this. Otherwise, we'll increment I will be next I to I plus 1, next value of the bacteria. After that, it will go to step 3. Step 3 here is again computation, tumbling. Now one more thing which here I want to tell, like for any function value, we take J plus 1 will be what? J, this is K, this is L. Next chemotactic step will be equal to what? This will be equal to previous chemotactic step, that is J comma K, comma L plus the CI. CI was what? It was the step size of the swim, or about what area the bacteria is making a swim. These earlier position and the CI position, these two positions combined will give the new value for the chemotactic next step. Now increment, if I has been checked, if all the bacteria are covered in this search space, now what will it look for? It will look for if all the J, that is the chemotactic steps, are, it will be incremented by 1. First chemotactic step is over for ith bacteria, then second step, then third step, and then it will increment bacteria. Now this was the previous result. I will settle for 1. Compute J health. Now in these two slides what we have covered, this is like initialization, initialized, evaluated, this is made a tumble or swim, this has updated its location, new location value, and coming on to here the third and the fourth step will be performed now, that is reproduction, and this is elimination and dispersion. After the healthy bacteria has been calculated, we'll again check it for it has reached completed its search space or not. Now this is sorting of half of the healthy bacteria and half of the unhealthy bacteria. With this step, we'll now reach to K. K was what? Reproduction step. If half of the unhealthy bacteria have been deleted from the complete group of bacteria which we are talking about, we'll increment our reproduction step again. If now after each increment we have to check it for these 4-5 values which we had initialized, these values NC, NS, NR, NE, ND. After each increment we have to check these. Now it has incremented for K, it will check if K is less than NS or not. If it is less, then it will lead to a 0 value. Otherwise, again starting with the first pixel, it will eliminate, check for its elimination has ended up with the entire search space area, and then it will increment L, that is elimination and dispersion. Finally, if our L is also less than ND, that is number of elimination dispersion steps, if L is also less than that, will return the bacteria with the lowest value of the cost function. That was actually the main aim of the foraging optimization technique over here, and then end the complete system. Now talking about advantages, less mathematical complexity. It might look big when we talk about the complete flow diagram, but there are basically just 4 steps which we have talked about: NS, NC, NRE and NED. Fast conversion, since we eliminate 50% of the unhealthy bacteria, accuracy and widespread applications. BFO is largely not affected by the size and nonlinearity of the problem. This is also used in fact AC devices. Like we can talk about it as being used in image processing. It is on the parallel being used in the terms of electrical, like students, they can also use this optimization and they work upon for their thesis because it is used in fact devices. These are flexible asynchronous transmissions. For fact devices, there is large scope nowadays, and there's also uses optimization techniques like BFO, which we are talking about. It converges to the optimal solution in many problems where most analytical method fails. I have quoted some few papers in which they have proved it with all the analysis that BFO and adaptive BFO, these both techniques are much more optimal solution providing than in comparison to generic GA and PSO algorithms. Applications. It has drawn attention of researchers as a high performance optimizer, and it has successful applications in following areas. It is used in PID controls, hence we can say it is optimum control engineering. Image processing, like denoising filters for human intestines, it is present. We'll use it as denoising of the many diseases. Network scheduling, it is used in electric load forecast. BFO coupled with methods of moment, MOM, it has also been used in antenna applications. Nowadays, many antenna applications are employing these optimization techniques, and even in fact devices. MOM is method of means, moment of means. The moment of means is basically the average power of each random variable. We decrease that power in the random variable and make it optimize. the first application is SABFO, that is self-adjusted BFO. This is a variation of BFO only, and it works much more accurately than BFO when applied to RFID, radio frequency identifications, network scheduling. The simulation results when compared to GA and PS approved superior solutions. With each of the application, I have mentioned 7, and with this 7 references from where the papers these have concluded. Applications of bacteriophagocytic optimization, it is used in neural networks. In the starting I told it is used in all the soft computing techniques using fuzzy logic, neural networks, artificial intelligence. For short-term electric load forecast, simulation results also showed BFO converges more quickly than this is generic algorithm neural networks. It converges, it takes much less time as compared to GA neural network. BFO is applied to antenna problems. In antenna problems, how this is applied, it optimizes the directivity, taking inverse of it as the cost function. We need to minimize the cost function. It takes directivity as the inverse and do the optimization. It is capable of synthesizing patterns with multiple nulls at desired directions, that too with fast convergence. Again, this fast convergence, and this is used in antenna applications where we need the multiple nulls at a desired direction so that beam width does not spread and we get high bandwidths. It is used to calculate resonant frequency and feed point of microstrip antennas, which many people are working on. This is also using BFO as its optimization technique for the thick substrate values to make the frequency in resonance with the actual input frequency. It is used in image enhancement tool for reconstructing high quality of images in less times. In fact devices, this is used in achieving the minimization of the real power loss. The total power loss in the devices at the transmission sites we need to be minimized, and this is the fact devices BFO is used with total cost is also minimized, voltage profile is improved, and voltage stability is being achieved so that transmission does not cause a problem to even the longer distances. Now, these are certain references for RFID. This was RFID network scheduling used in adaptive bacteria foraging algorithm. This was in one of the journals of computer sciences. And bacterial foraging optimization for neural networks, which we have talked. For dipoles of high directivity in antennas, and convergence antenna array faster convergence, and rectangular microstrip antennas, and these are the adaptive filters to enhance the signal to noise ratio in an image. Thank you. Any queries, please?
Maharaja Surajmal Institute. Yes, we have any question?
Hello.
Yes,
Good
ma'am.
afternoon.
Good afternoon, ma'am.
In reproduction, you are taking only the sorting the function value on the basis of minimum value.
Yeah, on the basis of cost. Yes, ma'am.
In reproduction process, you are starting the function value on the basis of minimum value.
On the function of the minimum cost value that we have estimated. We actually decide the J last function and update it with the comparison to the next pixel. Once we have updated the value with the next pixel and compared it, and we have sorted out the lower cost value, then why we need to again keep it in the image and reprocess it again, saving our data, and even convergence rate will increase if we'll do so. Hence, on the basis of the cost function, we are cut shorting the 50% of the half unhealthy bacteria.
So in initial, what is your population in initial step?
Initial population, it will depend upon the size. Total search space S is M cross N. It will depend upon the image resolution that you take. It will be varying up according to that. That is, the population is the size of the image.
No, so after reproduction, what is your population? First,
it will be 50% of that. It will become 50% of the actual input.
50%.
Yes, okay, ma'am. Anyone else?
YMCA? Hello at YMCA? Do you have any question, ma'am?
Any queries?
Yes, Maida.
Hello.
Yes, ma'am.
Yes, hello.
Yes, ma'am.
Hello, I'm speaking from JSS Engineering College, Noida. Hello.
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 Hello. Yes,
Yes,
I'm.
ma'am.
Yes, sir, you
Hello.
are audible. Ask your
Yes,
question.
sir.
Yes. Is this bacteria foraging is applied for the classification problem or only for this prediction or estimation?
So please,
Is this
so for
optimization technique?
class, so it
Hello.
is basically for image enhancement. It is used as image enhancement tool. It is used as denoising as an image filters. But for classifications, I have not seen any paper in that case. I have shown all the links of the papers that I have used for this session. For classification, I don't know, and I have not seen it for the papers of the 12 papers I have seen.
Okay. Thank you. Thank you.
Okay, sir. Thank you, sir.
Okay, thank you so much. They're all working, these three of the students, they are all working with this optimization techniques, and they have just tried to describe you that what are the optimization techniques, what are the algorithms, and some applications to which they are working upon, that they have produced. Some are working on segmentation, some is working on denoising filter, right? So they have produced their their concepts and their work, that how they are using in case of this filter, denoising filter or segmentation. Now if you want to use for other applications, you are definitely free to do it. You can just find out that what are the applications where you can use this optimization. So in this session, actually our aim is to give you the description of the optimization algorithm and what are the different types of applications where you can use it. So I'm sure that you must have got the benefit from these sessions. Now let me give you some, and the first class only I have given some assignment to the all the remote centers, and the remote center coordinators are were asked that they have to take the coordination part. So I had told the remote center coordinators to group some some participants and to decide some research papers. So now the time has come. So today we will complete it now only, that is on at 3:30, and you will get enough time today and tomorrow morning at 9:30 to 10:30 or 11 o'clock. I will take some MATLAB programming or the research problem solving with the MATLAB programming. I'll just discuss, and after that we will definitely float the questions to the remote centers, and you are one or two groups can discuss that what are the papers you have studied and what are the the concepts you have studied, and how you think that those papers which you have studied that can be implemented, and how what are the processes you have studied and how it you can go through it. So you can give the light of that what are the the contents, abstracts and conclusion of that paper which you have read within this 4 or 5 days. And after that session we will continually we will just do the valediction of the course after 10 or 15 minutes. So 9:30 to 10:30 or 11 o'clock I'll take the session on MATLAB programming, and after that you will be free to share your views, because within these 5 days something you must have learned. And I will want to know that what is the your idea and how you will go in future in research work. And after that we will do the valediction, and the feedback forms I have sent to all the coordinators. You must have got the feedback forms, so please tomorrow the coordinators are requested to fill up the feedback forms from all the participants, and when you will send the bill to us, all the feedback forms should be you should send to us. And now finally 3 centers are connected with us. The DIT Dehradun has been rejected because they were not continually attending, and so 3 centers are with us. One is your Maharaja Surajmal, another is your JSS Noida, and third one is your YMCA University. So these 3 centers are requested to work on those research papers and just to prepare yourself for some questionnaires or something, that sharing your views. It will be recently, this is not anything examination point of view or something assessment point of view. This is just that if you share something, that it will be beneficial to each and every participant who are attending this course. So minimum 4 or 5 papers if we can share, then it will be very much beneficial, so that you can give to work to your own students also, or you can work yourself also in that field. So thank you so much. And any questions or any feedback from the centers?
Hello, ma'am.
Hello, yes.
Kindly send the PPTs, all the PPTs, to our coordinator, Maharaja Surajmal College.
I'll send.
So that we can study and relate to our research papers.
Research papers completely will be, that will be very much independent of this, PPTs, because research papers you have to search yourself corresponding to your artificial neural network. For example, if you want to do in clustering, or if you want to do in classification, or if you want to do in optimization, or if you want to do in backpropagation. So that type of Google, you can just search in the Google for the papers, then you can search, you can study the papers. But PPT, definitely all the PPTs will be sent to each and every coordinator.
Okay, ma'am, kindly send it today only. So thank you.
I'll just check it up. Okay. Anything else? Okay. Then tomorrow at 9:30 again we will meet, right?